Ngalakin Khadijan Nyunga Boja.
Good afternoon. We'll make a start. I'll give a couple of minutes. There are a few people outside. Normally our postgraduate showcase is held at the Baileys, so a lot of people still think it is at Baileys, so there may be a few latecomers. Good afternoon, and welcome to the UWA Institute of Agriculture 2020 Postgraduate Showcase. We call Frontiers in Agriculture because it's all coming from the PhD students, cutting edge science and technology being done in this university. Well, as a traditional way of acknowledging the traditional owners of the land. Before we get started, it is customary for the University of Western Australia to acknowledge that it is situated on Noongar land and that the Noongar people remain the spiritual and cultural custodians of their land and continue to practice their values, languages, belief, and knowledge. I would like to acknowledge members of the UWA Institute of Agriculture Industry Advisory Board, distinguished guests, university colleagues, students, ladies and gentlemen. So once again, welcome to the 14th Annual Postgraduate Showcase since the re-establishment of the UWA Institute of Agriculture back in 2007. So it has been an annual event. We have secured a larger venue this year to adhere to the university's COVID-19 requirements. So if you have not already done so, please ensure that follow the social distancing rules. I don't know what it means. And use the hand sanitaries we have provided both on the left-hand side and in the front. I'm proud to say that the Institute integrates research, education, training and communication in agriculture and related natural resource management areas across 4 faculties of the university. The Postgraduate Showcase brings together some of UWA's best PhD students to share their research in agriculture and related areas. Normally, these students are at least halfway through their PhD program, or some of them are just finished. So they have something solid to convey to the public, industry, and community. Now it's my pleasure to introduce the chair of this session, or inaugural chair. It's my pleasure to introduce CBH Group Chairman, Mr. Simon Stead. Simon was appointed as the Director of the CBH Board in February 2015, as a Deputy Chair in April 2019, and as Chair in April 2020. Congratulations, Simon. He's currently a member of the Remuneration and Nomination Committee. Simon runs a mixed sheep, cattle and cropping operations in Cascade and Dalyep in the Esperance Port Zone. I have visited those farms a number of times. He's a member of the UWA Institute of Agriculture Industry Advisory Board and a founding member and past chair of the Association of Sheep Husbandry, Excellence Evaluation and Production. Simon holds an executive certificate in agribusiness, marketing from Monash University, and is a graduate of the Australian Institute of Company Directors. Please give him a warm welcome. You want to use this one? Just plug in.
All right. Thanks, Siddique. Okay, I'm not sure whether that artefact at the end of the stand there is, if the speech is no good, I'll be hanging from that when we're finished, but thanks Professor Siddique for your invitation to speak today and to open the Institute of Agriculture 2020 Postgraduate Showcase. It is a privilege to be here today amongst such esteemed company who are focusing on advancing agriculture, Australia's agriculture and resource management sectors. Before I begin, I too would like to acknowledge the custodians on this land on which we meet, the Nyungar people and their elders past, present and emerging. When I was invited to speak today, I was told that this year's showcase would reflect the interdisciplinary nature of agriculture. This led me to reflect on our industry, our purpose and how we come together across all different skill sets to produce the world's food. Often consumers, particularly consumers in more developed economies, take for granted the effort and the science required to provide food that we enjoy every day. Take the task of getting a loaf of bread to the family table, for example. From a very simplistic view, there are 5 players involved in this process: the farmer, the supply chain, the processor, the wholesaler distributor and the retailer. Each of these players must hire employees and build businesses, which in turn must work well together, safely and efficiently, to get a family a loaf of bread when they want it, at a price they are willing to pay. For farmers like me, we grow the wheat, which is ground into flour for the bread. To do this, we need key inputs such as seed, fertiliser and chemicals. And this is where the role of our agricultural scientists, those of you in the room, is critical. The importance of science, of seed breeders, soil scientists, chemistry specialists as examples have on producing this loaf of bread cannot be underestimated. Each have a part to play in producing the end product. Like all tasks though, there are challenges. You might produce a seed, but will it respond to the weather conditions? And will it yield and produce the quality required? And most importantly, will people want to consume it? These are the questions that take a significant amount of time and research to fully understand. And the answers to these questions build the foundation of this industry and the food that is produced. Next is the supply chain. And in grain and in WA, that is where CBH comes in. As producers in an export-dominated state, our growers are extremely reliant on the CBH logistical supply chain and marketing arm to realise value for the grain by getting it from their farm to the international customers. To remain successful for the long term, we must ensure our growers can remain internationally competitive and hold their own on the world stage. This means low-cost outbound logistics and a safe and efficient and reliable supply chain that maintains the quality of grain throughout. Increasingly, changes in macroeconomic and political environments are having an impact on agricultural supply chains across the world, including CBH's. As many of you would be aware, there have been trade tensions between Australia and China recently, and CBH, unfortunately, has been one of the entities at the centre of some of these issues. Despite the position taken by China, through science, from the very first seed to the quantification of very exacting standards, we are very confident that the grain we export meets the requirements of our customers, whether it is barley, wheat or other products. That is what we pride ourselves in as West Australian farmers and as an industry from beginning to end. Now, coming back to the family's loaf of bread. Similar to the supply chains, processors must also focus on cost, efficiency, quality and meeting customer specifications. Typically, wheat goes to a flour miller to make flour, and then the flour goes to a commercial bakery to be made into bread. Once the bread is produced, it is provided to the wholesaler or to the distributor to sell on to retailers. Wholesalers and distributors need a network to distribute the bread, while retailers need access to consumers, whether bricks and mortar or online. It's only then, and after all of this occurs, that a family can walk down to a local shop to buy a loaf of bread, most likely completely unaware of the number of people involved and the skills required to get it there. I've gone through these simple steps today to demonstrate the importance of each role we play in the agricultural sector. in providing food for people and to acknowledge those who are part of our great industry. We need to have people working on specific parts of this supply chain, from research through to retailing. And I admire the focus and dedication that is required at the postgraduate level to solve fundamental problems. Sometimes solving a single issue can have a cascading effect, leading to solutions across different disciplines. An engineering solution in a beehive may lead to solving a problem in the sheep's gut, which may answer questions about gluten intolerance in humans. University faculties at worst create silos, I guess. At best they create competition for resources and thinking. But again, I'd urge you to think that science has no boundaries. This is such an exciting industry to be in, and the breadth of opportunities is endless. In today's showcase, you will hear from those who are tackling issues and topics ranging from phosphorus efficiency in pastures, plant genetics, physiology and new technology and remote monitoring. To the agricultural students, engineers and researchers among us, today is a wonderful opportunity to recognise colleagues' hard work. I encourage you to continue advancing our industry, and I thank you for your efforts. Thank you. Siddique.
Thank you, Simon. Please be here for a while.
Yes.
Thank you, Simon, for that introductory remarks and some background about your company and how the grains move into the food chain and so on. And hope you will stay here for a while to listen to the talks. So this afternoon you will hear from 8 PhD students from 3 schools, I think 2 faculties or 3 faculties. The presentations are divided into 2 sessions with a short break in between for an afternoon tea, which I will let you know. Now it's my great pleasure to introduce the chair of the first session, Associate Professor Sally Thompson. Sally received her undergraduate degree in environmental chemistry and environmental engineering from UWA. She then worked as an engineering consultant for several years before completing her PhD at Duke University in 2006. She was appointed Assistant Professor of Surface Hydrology at the University of California in 2012 and promoted to Associate Professor with the tenure in 2017. Sally joined the UWA School of Civil, Environmental and Mining Engineering in 2019 and is the joint team leader for water for food production at the UWA Institute of Agriculture. So Sally's appointment is, some of you may know within the university, the Be Inspired campaign. As part of that, I think this is one of the best appointments made in the university to attract talents back to UWA, and I thoroughly enjoy working with Sally in that theme. So please welcome Sally.
Well, thank you, Siddique, for such a warm and positive welcome, and what a great pleasure it is to be able to act as chair for this first session. I'm going to get right to it and introduce our first postgraduate presenter, Mr. Daniel Kidd. Daniel is a full-time UWA employee and a PhD student who has worked at the Department of Primary Industries and Regional Development as a plant technician and researcher since 2003. Over the last 6 years, Daniel has worked on identifying morphological and physiological root traits that are involved in improved phosphorus acquisition efficiency in plants. He will be presenting today on improving phosphorus efficiency of pastures in southern Australia. Please welcome Daniel. I think that's all yours, mate.
Thank you, Sally. And thanks to the IOA for the opportunity to present today. And thanks everyone for coming out and supporting the students. Let's just move this on. Oh. Let's turn this on. There we go, we're on now. So as Sally said, I'm going to talk to you and ease you in today's program by talking to you about phosphorus efficiency in pastures of southern Australia. Now, she mentioned I was working and a student on this national project. You can see the collaborators up here in the corner, and these are my three supervisors down here who have helped me along the way, particularly with the writing phase. So let's get into it. Why is phosphorus efficiency important, and why would we want to study it? So for one, there's a price involved with fertilisers, and the long-term price of phosphorus has been increasing at twice inflation. And phosphorus fertiliser will make up a significant proportion of farm variable costs. And in our pastures, particularly permanent pastures, the efficiency of phosphorus fertiliser is quite low. So for every 5 units of phosphorus you put into that system, only one is actually exported in either wool or meat products. So it's actually quite an inefficient process, and the remaining phosphorus is actually tied up in organic compounds that are actually unavailable for plant uptake largely. A lot of the annual pasture legumes that we have in our pastures actually have quite a high phosphorus requirement compared to the other herbs and grasses with which they're grown. So you actually have to fertilise to the requirement of their requirements rather than those of the lower grasses and other species. So with fertilisers, there are environmental consequences from overuse. We can look at the Peel Harbour estuary in the southwest of the state. We can look at dairies in New Zealand. When you put on too much fertiliser and it runs off into waterways, you have problems with eutrophication. So we definitely want to improve efficiency from that point of view. And we have low input agriculture now, which is becoming a big thing. So you have organic and now regenerative agriculture, which really demands low synthetic fertiliser inputs. So you really need to improve the efficiency of your fertiliser use by your plants if you're going to really have productive systems. So the main premise behind this research was, can we find a forage or pasture species that has a lower requirement for phosphorus than some of the more traditional species that we use in our pastures today, and we don't compromise yield or forage quality. So this graph is quite simple, just shows that as you increase phosphorus fertiliser, you will increase yield. And some of our traditional legume options are represented by this dashed black line here. So as you increase the phosphorus, you get to about 90% of maximum production here, and it has this value of phosphorus inputs required. And we wanted to find something that fitted more of the dark blue line. So here, which reaches 90% of maximum yield at a lower phosphorus requirement. And this difference X, we equated could be almost a 30% saving in phosphorus fertilisers, which is quite a significant difference, and we thought it was definitely worth chasing. So we screened a number of commercially available pasture legume plants, and we found one in particular which is broadly adapted and already in commercial production. This is Ceradella or Ornithopus species, and you can see how it's grown there. And what's important to pick up is that graph that I showed you before. You can see the growth of subterranean clover. So this is one of the traditional options that I was discussing, and you can see where it reaches maximum productivity, around about 70 milligrams of phosphorus per pot in this instance. And you can see for Ceradella where it reaches maximum productivity at a lot lower input of phosphorus. And this is largely driven by morphological root traits. So it just has a more fibrous root system, explores more volume of soil, and can get more nutrients in that manner. So Ceradella are actually largely adopted in areas that are quite acidic, sandy, inherently of low fertility, and they don't really support species such as subterranean clover all that well because they have a high requirement. But they grow really well in these areas, and they've developed quite a niche environment. The problem with Ceradella is we can't just grow that everywhere across southern Australia and just reduce fertiliser inputs by 30%. So cultivar development of Ceradellas has really been focused on short maturity, medium to low rainfall zones fitting into crop pasture systems, particularly in WA where it's really successful. But we can see opportunities for growing such plants in permanent pastures which have high rainfall and longer seasons. But the problem is you can't put a short season plant variety into a long season growing environment because there's a lot of differences and the yield is impacted and they have a different flowering window. So it's just a square peg in a round hole. So it's just not going to fit. And there was a lot of problems with putting, farmers have tried putting these short season varieties into these longer season environments and haven't had a lot of success. So there's not a lot of literature around Ceradella with regard to the constraints that they're going to face in these higher rainfall areas. A lot of it is anecdotal evidence, and there is some scientific literature, but a lot of it is on cultivars which are outdated or superseded by new ones, a lot of these short season varieties. So the aim of my PhD in this project was to provide some scientific validation around some of those anecdotes. So 3 of those that I picked out were in the high rainfall zones. Ceradella will not tolerate waterlogged soils. So that's basically inundation of the root zone, there is no oxygen available to the roots, and productivity is subsequently impacted. Cool temperatures, farmers say, nah, it's too cold, Ceradella won't grow. So that was the other anecdote I wanted to check. And the other one is aluminium toxic soils. So I mentioned before that they will grow in acid soils. Acid soils are very low in pH, and at low pH you have a lot of aluminium in your soils, depending on your soil type. And Ceradella are universally supposed to be tolerant of aluminium toxic soils. So 3 anecdotes for which there was limited scientific evidence. So I'm hoping that this is universal. Everyone understands that these guys are the mythbusters, and they're going to help me along the way to prove or disprove some of the anecdotes. So first of all, waterlogging. Ceradella was not tolerant of waterlogging. I ran a hydroponics or solution culture experiment which grew plants for 4 weeks in nutrient-rich solution, and then had 2 weeks of a waterlogging period where half the plants had no oxygen available to the roots, and then we put them for 2 weeks in a recovery phase where they were reintroduced to oxygen again to see how they recovered. And you can see the plants up here. The plant on the left is a control, and the plant on the right is a waterlogged plant. So this after 2 weeks of waterlogging, and you can see the impact that it has on root growth for yellow Ceradella, French Ceradella, and this is a waterlogging tolerant species which is somewhat not impacted. And if we look at that graphically, on the y-axis here we have the root dry matter, which reflects the roots. You can see there on the right. This is the initial 4 weeks of growth, the waterlogging and the recovery phase as I discussed. And you can see for yellow and French Ceradella, as soon as you introduce the waterlogging treatment, root dry matter is reduced, and that subsequently affects the shoot dry matter. And when you put them into a recovery phase, they don't recover particularly well, and they never actually make up that ground. Whereas if you look at a waterlogging tolerant species like Balansa clover here, we can see that not impacted by waterlogging, and actually in the recovery phase, waterlogged plants actually have higher root dry matter than the controls. So that's more what a waterlogging tolerant species looks like, and yellow and French Ceradella looks nothing like that. So in this case, we can say the anecdotal evidence was somewhat accurate. So moving on to cool temperatures then. Ceradella productivity was not reduced by cool temperatures. And I tested this a number of ways, and the first was to grow them in temperature cabinets. So I grew about 30 different cultivars, old and new, in 4 different temperature cabinets and compared it to some of the traditional pasture legume options I was discussing earlier. And you can see what an effect temperature has on dry matter productivity. As you increase temperature, you increase growth rate and you get more dry matter production. However, when we put this in a graph, it wasn't the same for all species. So I have up here Lucerne versus a Ceradella variety. On the y-axis we have shoot dry matter, and across the base here we have the different temperature cabinets. And you can see for Lucerne, as you increase the temperature, you increase the dry matter. But for Ceradella, there's actually a drop-off at the high temperature treatment. Now in this study I found there was actually no difference in shoot or root dry matter amongst any of the species at cold temperatures, but it's actually at the hot temperature where there was quite a significant reduction for all Ceradella varieties. So we could actually say that not only is it not reduced by cool temperatures, it's actually impacted by warm temperatures, so the complete opposite of our anecdotal evidence in this case. So when I tested this, I looked at how fast these plants are going to come out of the ground under cold temperatures. So these are the 4 different temperature regimes again, and I measured germination and emergence. So germination is just when the seed is under the ground and it puts out its first little root or radical, but then a lot can happen to the plant as it emerges from the soil. There could be a number of pathogens in the soil or a lot of interactions, so it might take them a long length of time to get out of the soil. So we also measured emergence. which is when you put up these cotyledons that you can see here. And the main things to take from this graph, we have cumulative germination and cumulative emergence from the soil up to 100%. And the 4 different temperature regimes you can see here. And again, comparing Ceradella and Lucerne. And the main takeaway is these little black lines here. So I put the 90%, where 90% of the plants either germinate or emerge from the soil. And you can see for Ceradella that they will germinate within about 5 days, and Lucerne will germinate within about 8 days. Emergence is about 12 days for Ceradella, and probably 13 or 14 days for Lucerne. So Lucerne is about the fastest plant I've ever seen grow as a forage species. So we can definitely say that Ceradella is not impacted by cool temperatures at germination and emergence. So I thought, well, let's grow older plants. Maybe the difference is in older plants. You know, let's not completely rule out the anecdotal evidence here. But again, when I grew older plants, I found the same situation. Cool temperatures weren't actually having an impact. In fact, all the species that I grew, there was 2 yellow and 2 French Ceradellas, Lucerne and subterranean clover, my traditional pasture option. And there was no differences at, there was no differences at the cool temperatures, except for about 49 days of growth where Lucerne started to kick away. It was actually at the high temperatures again, where you can see Lucerne really kick away. Ceradella doesn't respond any differently to subterranean clover. So again, it's not really the cool temperatures which we have to worry about, it's more the hot temperatures. So for this instance, anecdotal evidence wasn't stacking up. So maybe not quite accurate. So my last bit of anecdotal evidence was Ceradella is universally tolerant to exchangeable aluminium in the soil. So all cultivars will be tolerant of aluminium. And I ran this in solution culture, had basically increasing levels of aluminium, and measured the root length or root response, because aluminium in the soil will impact the roots and reduce root growth, which will subsequently impact the nutrient uptake and reduce productivity of your plants. However, when I grew it in solution culture, we had some variation. So we have here 3 Ceradella varieties. Some of them were quite tolerant, some had moderate tolerance, and some, if you gave them a sniff of aluminium, would reduce root length very, very quickly, so quite sensitive. So it was actually quite a lot of variability for aluminium tolerance, which was not quite what I expected. So the results are suggesting otherwise as far as that anecdotal evidence would suggest. So I thought, well, this is solution culture. I like growing plants in the field. How are they going to go in soil? I should really test this in soil. So I went out to Meriden, I dug up some soil, and this was a soil type which has a nice loam over the top with a very highly aluminium toxic, nutrient deficient subsoil, which is quite common. They're called wodgel soils. And this is what it looked like when I reconstituted it in a pot. Now, quite clearly, when I grew the plants just in topsoil, so just this nice brown loam here, they grew very well. When I grew them in just the subsoil, they wouldn't grow. So clearly they were not very happy with that subsoil at all and wouldn't grow. When I put them in, reconstituted the pots like this, they had 70% of the roots in the topsoil, 30% in the subsoil, and they grew as well as if they had all topsoil. So this was kind of unexpected, and this is one of my more sensitive varieties that I identified from my solution culture experiment. So if even sensitive varieties are growing in a wodgel soil type with aluminium toxic subsoil, then maybe my solution culture experiments weren't quite right. So I thought, well, let's take this one step further. Let's go all the way to the field. So I thought, I'm not going to do it in a pot. And the IOA have a Callan-Up scholarship which helps with these kind of field experiments, which was very useful. Thank you very much. And allowed me to do this. So I grew Ceradellas ranging in aluminium tolerance based on my solution culture experiment. We have here French Ceradella cultivar Cadiz, the most sensitive in my solution culture experiment, and produced the most shoot dry matter of any cultivar at this site. I grew the plants without lime or with lime, so lime will increase pH and ameliorate the aluminium problem, but it didn't matter what I did, shoot and root dry matter did not vary between unlimed and limed for any of the Ceradella varieties, whether they were sensitive to aluminium or not in my solution culture experiments. So, that was a little bit annoying, and I suppose the jury is still out on this one as far as aluminium tolerance in Ceradella is concerned, but certainly they can grow in aluminium toxic soil types if it's a subsoil constraint. So I'll just conclude with a few comments. Ceradella will tolerate cool temperatures and acid soils, but it will be affected by waterlogging. So going into high rainfall regions will be a problem if waterlogging is involved. There is certainly scope for increasing the adoption of this species in areas where it is not currently utilised. But sometimes anecdotes might be inaccurate or misleading. I think we have to be a little bit careful about those, and they might unduly limit the adoption of some species. I'll leave it there. There's a lot of pretty pictures and a lot of graphs. There's a lot more information I can tell you, so if you want to hear more about it, come and find me at the tea break. Thank you very much.
So we have 5 minutes available for questions for Daniel. Would anybody in the audience like to offer him one? And he's in trouble if he's not, because I have any accent, so front of the audience, please.
Hey, Louise.
Thanks for your presentation, Daniel. I enjoyed it. Regarding the field studies that you did out here to look at the tolerance of the Ceradella soil acidity, what was the year like? Because
Good.
if I'm wrong, if the plant roots, if they can avoid getting into the water or subsoil, then they'll hang out in the surface soil, especially if there's enough moisture. So does this, you need to go out there with another season where things might get moisture?
Yeah, that was kind of my theory, was that they're actually finding everything they need in that topsoil and not actually heading into the subsoil at all. So I did actually do some deep soil cores at this site just to measure soil moisture. So I thought if I can measure how much moisture they're using at each of the depths, then maybe that can be a proxy for how deep they're putting their roots into the soil. But I didn't find a lot of difference between the cultivars. But I did notice that for French Ceradella, which was probably the more aluminium sensitive of the two species, that the seed yield was actually reduced. So I'm not sure if that's because it couldn't get into the subsoil to access more soil moisture, because it couldn't get into that acidic aluminium toxic soil, whereas the other species did and didn't seem to suffer, because I think it was a really dry September when they were in peak flowering, and seed yield seemed to drop off for only French Ceradella but not yellow Ceradella. So it could be due to that, but I can only dig so deep because I actually dug up shoots and roots. So I could only go too deep, and I kind of hit that, subsoil. So there's only so much you can do in a field experiment, unfortunately. I can't tip it out like a pot.
Daniel, in areas where there's more loamy soil, is that an inhibition in itself or clay soil in any way? And in other words, do they have any other restrictions on growing in the areas which would be climatically suitable?
Yeah, I think, the climatic suitability, the CSIRO did a climate adaptation model for Ceradella, and it was basically the same as subterranean clover, which is our most broadly sown and adapted pastoral legume in southern Australia. So there's no reason it can't grow in high rainfall regions, and I think a lot of the older cultivars were particularly suited to those kind of regions, and I mentioned the narrowing of our focus to kind of short season varieties. As far as clay soils go, I think there is evidence to suggest that they don't do all that well in clay soils, but certainly loams, I think they're fine. And I think as long as the soil seems to be free draining, it doesn't, they'll grow in high rainfall regions. And I've grown it in Denmark, for example, which is quite a high rainfall area, and it wasn't restricted by clay, but I think if you have waterlogging as an issue, if it holds a lot of water, that will be a problem. But I think as long as it's free draining, it should be fine. And I've read reports of them growing in clay soils before and doing really well. So I think we have to be careful about the over the fence conversations limiting adoption sometimes. Yeah.
Well, in the interest of time, let's thank Daniel again. Daniel, here's a certificate. Thank you for your
Sally.
participation. It's nice to meet you. Great work. Thank you.
Thank you very much.
I'm hearing about Ceradella, so it's really interesting to hear what you're up to. Cheers. Our next presenter is Kirill Sukhoverkov. After graduating from Lomonosov Moscow State University in 2015, Kirill worked as a research assistant at the Chemical Enzymology Department. In 2017, he moved to Perth to join Dr. Joshua Milne's research group at UWA, focused on finding new modes of action for herbicides and characterising the targets of existing herbicides. He will be presenting today on predicting herbicides from phys-chem parameters. Please join me in welcoming Kirill.
Good afternoon, ladies and gentlemen. The previous speaker told you about how make the plants we want to grow growing. I will tell you an opposite story about how to kill the plants you don't want to grow. In other words, we will talk about weed control. Weeds, also known as unknown vegetation, undesirable vegetation, are the big threat for agriculture. When weeds are not controlled, they can reduce crop yield to zero. Therefore, we need to apply certain measures of weed control, and one of them is spraying plants with herbicides, the compounds which are toxic for plants. Herbicides are very cost and labor efficient measure for weed control. However, herbicides are not a silver bullet. Since they were introduced in agricultural practice, the herbicide resistance was an ongoing issue. On average, there was around 2 decades since the new mode of action introduced, and then you have resistant weed. And therefore, there is a constant need in introducing new modes of action. But for the last 33 years, till 2019, no single new mode of action was introduced. Therefore, we need to search for herbicides everywhere, even in some unusual places. And one of these places are antimalarial drugs. In early 90s, it was found that due to close evolutionary relationship between drugs, between malaria parasite and plants, a lot of herbicides are antimalarial. In our lab, it was found that opposite is also true, and a lot of antimalarial drugs are herbicidal. Therefore, we decided to explore a drug library, Malaria Box, which is targeted against malaria parasite, to find some new herbicides with new modes of action. This library contains 400 drug-like molecules, and none of these molecules are approved for human use. Therefore, if you find any attractive herbicide, you can use it straight away, without any problem with intellectual property. To find herbicidal molecules, we screened it against our model plant, Arabidopsis thaliana. We led this plant to germinate on agar plates in the presence of antimalarial compounds, which I will further refer as MMB. And we were looking for typical herbicidal symptoms, which included bleaching, retarded growth, or failure to germinate. And we found that, very excitingly, 1 out of 8 compounds possessed at least one herbicidal symptom. But plants don't grow on agar plates in real life. They grow on soil. And then we decided to test these candidates against soil-grown Arabidopsis. And what we have found? Only 14 molecules were herbicidal, less than 5% of the whole library. It was quite a sad situation, but it's not something unusual. Same story happens in the field of drug discovery. Out of 100 candidates which are active in vitro assays, only dozens will work in model organism. And the reason is that to be active in a model organism, compound has to be bioavailable. And to be bioavailable, it has to have molecular properties which have to fit within pretty strict rules, which are known in the field of medical chemistry as rules of 5. It postulates that a compound should have molecular weight less than 500 Daltons, have partition coefficient, it's a hydrophobicity parameter less than 5, hydrogen bond donor count less than 5, a hydrogen acceptor count less than 10. And then we asked ourselves a question: what if same kind of rules exist for herbicides? And to find what these rules are, we explored molecular properties of 355 commercial herbicides. And we found that herbicides also have their molecular properties falling within pretty narrow limits. And these limits are quite similar to the rules of 5, However, unlike drugs, herbicides have lower molecular weight and lower hydrophobicity. Then we assumed, what if antimalarials failed against soil-grown plants because they are complete outliers of the herbicidal rules? But it's not the case. As you can see from these cluster plots, where antimalarials are shown as blue circles and herbicides are shown as red circles, antimalarials fit pretty nicely within these limits. However, antimalarials are on average heavier and more hydrophobic. But it's no wonder, because the antimalarial library was optimized for human use, not for plant use. Therefore, we assumed, what if some parameters are more important than others? And we compared the set of molecular descriptors among the plants which were active against soil-grown Arabidopsis and those plants which were active only in the initial screen. These descriptors included parameters which characterized flexibility of molecule, its aromaticity, hydrophobicity, and solubility. And we have found that none of these parameters are different between soil-active and soil-inactive antimalarials. But there were two parameters which were different. One of them is partition coefficient. Partition coefficient is the parameter which characterizes hydrophobicity of ionized form of molecule. In other words, the higher is the value of partition coefficient, the more comfortable molecule feels in oil. If it's lower, molecule feels more comfortable in water. And we have found that for antimalarials which were active against soil-grown plants, the partition coefficient was lower and closer to the average value for commercial herbicides. The compounds which were not active against soil-grown plants, they had higher hydrophobicity, around 4. The difference is close to 1, but it's quite big difference because partition coefficient is a logarithmic value. Therefore, actually, the hydrophobicity of molecules which failed against soil-grown plants is 10 times bigger than those which succeeded. So, we concluded that less hydrophobic molecules are more likely to be herbicidal. Another important parameter is the charge of molecule. Herbicides, same as drugs, they contain a lot of ionizable groups. However, only two-thirds of commercial herbicides, they are neutrally charged. Roughly one-third has negative charge. And literally 2 herbicides out of 300, only 2 herbicides have positive charge. It's paraquat and its analog diquat. Similar situation was found for antimalarial drugs which were active against soil-grown plants. The majority of them were neutral, few were negatively charged, and only 1 molecule was positively charged. But for the compounds which were active in initial screen but failed against soil-grown plants, the situation was opposite. While maybe a little bit more than half of them were neutrally charged, they had unusually high proportion of positively charged molecules, around 30%, 30-40%. Therefore, we assume that neutral molecules or negatively charged are more likely to be herbicidal. After this, we assessed if it's like a really good assumption that antimalarials which are active against soil-grown plants fit better within herbicidal rules. We scored the molecules based on how well they fit from 0, which means a molecule is complete outlier and doesn't fit any rules for herbicides, till 18 score, which means it precisely fits. We have found that the average score for herbicide similarity of antimalarials active to soil plants was similar to commercial herbicides, around 14 points, while the molecules which failed against soil-grown plants, they had a score of 12 out of 18 points, which is a statistically significant difference, and it's 2 points less than average value for herbicides, which is 14 points. It's not something surprising that herbicidal antimalarials are more close to herbicide, but another question is more interesting. If higher similarity to herbicide means higher chance to be herbicidal. And then we compared the proportion of antimalarials active against soil plants among compounds which were scored above average value for herbicides and below it. And more than half of compounds which were scored 14 or above points were active against soil-grown plants. In contrast, the antimalarial score below 14, 80% of them were not active against soil-grown plants. Therefore, we can assume that higher score means higher chance to be herbicidal. After this, we decided, it was an interesting question. If we can apply our knowledge that a lot of antimalarials are herbicidal and molecules which are most similar to herbicides, and find some herbicidal antimalarials by in silico screening. So I applied these scoring rules to the set of 631 antimalarials which were optimized against liver stage malaria parasite. At liver stage, the physiology of malaria parasite is quite different from blood stage. Therefore, we hoped to find a compound which will be herbicidal and has some new unusual mode of action. I calculated the molecular descriptors for these compounds and found that 120 of them were scored 14 or above, which is quite high proportion. 39 of these compounds were active against malaria parasite. It means we can hope that they have some target in plants. And 6 of these compounds were active, 6 of these compounds were available to purchase. I bought them and tested against soil-grown Arabidopsis. At this diagram, I show you the result of herbicidal test. The compounds were applied either before Arabidopsis emerged, it's shown in pre-emergence row, or compounds were applied to Arabidopsis seedlings after they emerged. It's post-emergence row. I used commercial herbicides glyphosate and oryzolene as positive controls. And what we have found, that compound 5 has quite high herbicidal activity. It completely inhibited growth of Arabidopsis if applied at 100 mg per liter application rate pre-emergently, or 200 mg per liter if you apply it post-emergently. It was quite comparable with commercial herbicides. Compounds 1, 2, and 6, they were moderately active post-emergently, but were not active pre-emergently at all. Compounds 3 and 4 were not active at any stage. And the possible reason is that compound 3 and compound 4, they share the similar structure. And probably they are not active not because their parameters are not suitable, but just because they don't have a targeting plant. The compound 5, we didn't find any structure analog among commercial herbicides for compound 5. Therefore, we decided to make physiological profiling of it, to find out what if it really has new mode of action. And this job was done in collaboration with BASF. They made more than 13 physiological assays in order to figure out which physiological processes are affected by compound 5. And they found that compound 5 is a weak inhibitor of photosynthesis. It has moderate oxidative phosphorylation uncoupler activity, like herbicides Dinesep, which is not really used now. But it doesn't have any effect on respiration and carbon assimilation. Whereas uncouplers, usually they have effective compound as uncoupler, it will affect respiration and carbon dioxide assimilation. And this physiological profile was compared with the database of BASF. This database contains more than 3,000 of physiological profiles for commercial herbicides and some reference compounds. And there were no match in this physiological profiling. And together with the fact that structure of compound 5 wasn't similar to any of commercial herbicides, we can say that it's highly likely to have a new mode of action. Therefore, the key point of my study is that we can use herbicide likeness to predict if compound can be herbicidal against soil-grown plants. We can use it to pick up compounds by in silico screening, and the future directions of my work will be to make some glasshouse studies of compound 5 against more relevant weeds than Arabidopsis, and then make structure activity studies for compound 5 to find if we can make it more herbicidal. Thank you for your attention. I would be happy to answer your question.
Fascinating work, and I'm sure there will be questions in the room.
So what are the next steps for
Yeah. For compound 5, next steps, we are going again in collaboration with BASF, test it against more relevant weed species. That's the work which is going now, and make some structure activity. So we will take the structure of compound 5 and try to change some side groups to see if we can improve its herbicidal activity and stability. And then we, of course, will continue mode of action studies, but probably apply some biochemical and structural biology methods. Yeah.
A different question. Are you able to publish this work because of the IP? Are you keeping it until you finish your PhD?
I'm keeping the structure not known now, but we have an industry partner in our lab, so we need to get approval of them, but manuscript is pretty much ready, and once they say, okay, you can publish it, then it will be published. And you will see all the details of structure and scoring system, which I have to keep secret now. I think the approach, like how it exists now, it's a useful tool, but maybe it's not that good. But we have a collaborator with artificial intelligence, and we are going to make it in conjunction more powerful tool to literally predict herbicidal from in silica data. Because now we still rely on a lot of experimental data. In terms of commercial application, of course, you try to diverse anti-malarial and herbicidal effect. For some compounds, because it's not the only compound we study in our lab, for some compounds, we managed to diverse these activities. For others, we didn't.
Given the negative media around glyphosate, would any of these compounds have any negative health impact?
Sorry? I didn't really.
Would you see any negative health impacts using these compounds as a herbicide?
Oh, I don't know now, but hopefully they will not. Of course, after we make it, first stage we're doing after we find some anti-malarial antibiotic be herbicidal, we test how good it works against bacterial malaria parasite. And then we will try to diverse activity, and if it comes ever close to commercialization, of course we have to make some safety tests.
Kirill, can I ask you a follow-up question there? We all know herbicides do not have the best public reputation. Standing at the very beginning of the process of bringing a new kind of herbicide potentially into our arsenal, how do you view, are there things you would maybe do differently to what people did in the 1950s to mitigate those public perception issues at the outset?
Yeah, the public, they don't even like GMO, so we know that GMO is wonderful. But maybe the best thing we can do is to make more thorough safety tests similar to something which is closed in pharmacy. And a good idea would be maybe to try to find some herbicides which will be very toxic to plant, but then they can be biodegradable. It's not some easy job, but hopefully we can find it.
You have the opportunity. How exciting. Thank you so very much.
Thank you. Thank you. Yeah.
Well, I'm very excited to welcome our third presenter, Mr. Jorge Silva Castillo, who is originally from Colombia. Jorge graduated from the Francisco de Paula Santander University with an electronic engineering degree. He moved to Perth 11 years ago to study English and a master's degree in microelectronics. Jorge is completing his PhD with the Microelectronics Research Group here at UWA, working on the fabrication of microelectrical mechanical systems, otherwise known as MEMS, microspectrometers. He will be presenting today on low-cost, portable spectral imaging systems for poultry industry applications. Please welcome Jorge.
Hi, everyone. Thank you for being here. So, you heard any electronic engineering? This talk will be more about applications. So the idea on this is focused on application of spectral imaging and image processing for farming applications. So the motivation of this project essentially is to develop a low-cost, universal spectral and 3D imaging technology for quality assessment of agricultural food products. So why is the motivation for this? Essentially, why this is important? Because in every stage of the food processing, we always want to make sure that the food we are eating is at the highest quality and is not contaminated. So most of these processes used for this kind of, for the chicken, poultry processing, usually are targeted for big companies, people who can afford expensive technology. But there is not available technology for the smaller farmers and the consumer, people who are really sensitive to, the price. So before I can explain how we're going to do this, so I want to thank the Buy West Eat Best Kim Chan Fellowship Award. It made it possible to start this project. This is a collaboration between UWA and Dr. Seon Cho at the U.S. Department of Agriculture. And as mentioned before, we want to create a portable and low-cost 3D multispectral imaging system. And initially, as my title says, the first proof of concept is to develop a system to measure volume of chicken and to detect fecal matter. So how do we measure volume? So we do this by mimicking the human eye. Essentially, we try to use binocular disparity. Essentially, it's by taking two images from two different cameras, essentially from two different views. So usually, if you put your finger in front of your eyes, you will notice, if you start blinking your eyes, that the image that's generated in your brain is changing in position. So you can notice that objects that are closer to the eyes or the cameras in the system will have a larger disparity, a larger movement relative to the side. For example, the left eye will notice that the object is on the right-hand side, but the right eye will notice that object to be on the totally opposite side on the left. But if those objects are further away from the cameras for the sensing system, you will notice a smaller disparity. It means that from this we can infer that objects that are closer to the camera are going to have a larger disparity, and objects away from the camera are going to have a smaller disparity. How can we use this? So essentially, we have two images and taken from two different cameras, left and right. And we identify some features, right? And then we estimate the distance from the edge of the image to the feature we want to measure. And from that, we can estimate the disparity, which essentially is the difference between the two distances. Then from that, we can build a disparity map. Essentially, that will tell us how far an object is from the camera, from the sensing element. So we can see that larger disparity is going to be represented by a lighter color in this image, which means this lamp on this visible image is closer to the camera. But this camera we have here is further away in the image, even though it's difficult to see on the visible image. So as you can notice in this area of the sculpture, essentially you will see there is a different color in the nose of the sculpture compared to the face. That means if we have a high enough resolution, we can estimate the small distances between the surface and an object, and from that we can estimate volume. So how can we build this kind of system? As I mentioned before, we are mimicking a biological system, like a human eye. So we need a brain, something that is going to essentially make all the calculation for the system. So we are using an embedded computer, the NVIDIA Jetson Nano. Essentially, it's a graphic processing unit that is specially designed for image processing, and it's very useful for accelerating, having real-time calculation. And for the cameras, essentially to replace the eyes, we're going to use two Raspberry Pi version 2 cameras. So why we use these kind of cameras? Because in terms of cost and the quality of image you can get, is one of the best in the market. But also, like the CMOS cameras, the one we have on your, on your phones or on your computer, are the most mature technology in terms of like, imaging calculate measurement. So by using these two elements, we implemented the algorithm in Python, and using the libraries for OpenCV, which is a library for like image processing that offer like the already implementation of the spectral or disparity calculation already. But our first experiment was like bad. We didn't have like a proper calculation of the camera, and essentially it's almost impossible to distinguish anything. But under the supervision of Dr. Shamshad at the U.S. Department of Agriculture, we improved that calibration of the system. We were able to identify objects within the images taken using the system. Obviously, this needs more improvement in order to calculate volume, but it's a good starting point. Then, moving on to how we can measure different properties on chicken. How can we detect fecal matter without being invasive or touching the chicken meat? We can use spectral imaging. Essentially, when you do spectral imaging, it's just extracting spectral information from the object you want to measure, and matching this information with the spectral signature of the object you are trying to detect. What is a spectral signature? Essentially, it's a unique spectral information from that particular material that either in reflection, transmission, or absorption. So how we can use this? So a simple example is red edge imaging or chlorophyll detection. Essentially, we built this system a few years ago. So we use it to differentiate any like green plants, anything that has chlorophyll from any green object. How do we do this? It's simple. Chlorophyll has a particular spectral signature, has a high reflectivity for the near infrared light, but has a low reflectivity for the visible light. So by taking two images on one of the bands and then calculating a ratio, we can estimate where there is chlorophyll within the image. So, but it's a similar process for like fecal matter detection. So a few years ago, in the U.S. Department of Agriculture, Dr. Shamshad, he led a project in order to simplify the process of fecal matter detection using only two bands. He used a line scan hyperspectral camera for this purpose. So this is an image of the experiment you can find on his paper. And from this, he concluded that by using two bands, one at 565 nanometers and one at 570 nanometers, and you're calculating the ratio from those two images, it's possible to detect like fecal matter with on top of the chicken skin. So we can see here the two images, and then this is the final image using the ratio. So what is the problem with this system? This, the hyperspectral camera he was using was especially designed for this experiment. It has a cost of about $100,000, something that is not affordable by everyone. So in order to avoid that problem, again, we are using a Jetson Nano in order to do the calculation for the spectral imaging. And we can use the same CMOS camera. You may be wondering, why do we use the normal cameras? Because the CMOS technology on this camera can detect visible light and can detect like near infrared light. So it can be used for a wide range of applications. The difference with the camera on your phone is that they have a special filter in order to inhibit the light that is present in the near infrared. So, but before doing the fecal matter detection, we had to do an object detection. Why? Because we are planning to use two cameras, and each camera we're going to have a different filter for the calculation of for the extraction of information on two different bands. And as I mentioned before, if you have two cameras, they're going to be like, you will have two different views of the object you're trying to detect, so you will have a disparity effect. So you will need to detect your object in order to do the pixel-to-pixel matching, and then proceed to match the two objects to calculate the ratio. Obviously, this is a work in progress, and I don't have any further results from this. So, again, I want to thank the BioWest Kim Chance Fellowship Award, because it made it possible to travel to US at US Department of Agriculture and get all this work done, testing the initial system, design improvement in the measurements under the supervision of Dr. Shamshad, and also we had an ongoing collaboration. We have like fortnightly meetings with Dr. Shamshad. So to conclude, so we are working on a development of a portable system for measurement of volume of chicken and fecal matter. We are planning to use like 4 cameras. We are planning to measure volume of chicken using a stereo camera pair, using a disparity or stereo estimation. The work we had to do in this area is to create a 3D point cloud map from the disparity map, and then implementing the algorithm for volume calculation. So we are also planning to detect fecal matter in chickens using spectral imaging from 2 different cameras. And for this, the work we had to do is essentially design and implement the algorithm for the fecal detection. And we need to design the measurements, how to take these measurements. As we are working with biological samples, we're going to chicken meat and fecal matter. So there are some special procedures for this kind of experiment. And as I mentioned before, and the more important part, this system has the potential to be implemented for other applications. So by doing a small modification. So as I explained about the chlorophyll detection, this system can be used to detect the volume of plants also, and how to detect like the level of chlorophyll within the plant, or you can use it to detect like defects in fruits that are not visible to the human eye. This is the end of my presentation. Thank you very much.
In the room who is now slightly scared about the prospect of chicken dinner tonight.
Ta-da.
Does anybody have a question for Jorge?
Yes. Well, I haven't read any literature. I mean, as long as there is a spectral signature unique to that particular plant, it is possible. Yeah, as soon as there is, I mean, at the end is finding like what kind of bands within the wavelength light had a different like characteristic. So you can shine light on that object and you get like a different characteristic from anything within the background. It's possible to detect it. It's just about finding that particular spectral signature.
In looking at fecal matter, we're obviously looking for negative effects. Are there any positive effects, you know, like state of ripeness or that type of thing that is used as technology?
Well, I'm not very familiar with the literature in that sense. But yeah, I'm not really sure about that.
Then you could find a red strawberry from a white strawberry, for example, in the field with similar technology.
Yeah, it's the same idea. The other question is like, as long as they have a different spectral signature, but I haven't read any particular paper that talk about that. You will need to find out about the spectral signature, and then you can apply it.
Jorge, I have a technical question.
Yes.
Show my stripes as another of the engineers in the room. I understand you're taking photos with 2 paired cameras, which will visualize a single plane. What do you assume about what's on the back side of things? So say you were actually an angel with a pair of folded wings behind you, and I took this photo here to estimate your volume, and I couldn't see your wings. I wouldn't get their volume. I'm confused about what you do on the back half of your chickens.
Well, so at some point you can estimate a shape for every like chicken. And from that, you can do an estimation and use, from the volume at the front, you can estimate the volume at the back. Essentially, you can estimate some roundness a similar way, and then you can get the estimation of volume. I mean, the system can be improved by having 4 cameras. Obviously, that's essentially a full 3D reconstruction. You take images from every angle in order to get like a full like 3D image.
So have you tested the effect or the uncertainty that you are incurring by...
We are still working on it. Yeah, Dr. Shamshad has done that. I think he has done like very good results. So the difference in his experiment, he used like very high quality, expensive camera lenses, and everything is in lab. So obviously it's difficult to compare with a low cost like chip system at this stage. Yep.
So do you think that eventually you can use it on a mobile phone and I can go to the supermarket and look at the chicken and say, I'm not going to buy that?
Well, I mean, I'm not sure that you can put it on your phone, but it's a potential application. So, so part of my PhD work is working on like a microspectrometer, essentially very small optical filter that can be tuned. So ideally, at some point, you can have a dedicated camera with a spectrometer. If you can take images at fast enough speed, you will be able to do all this with just one camera, at least the spectral imaging part.
Jorge, it seems to me that if you could mount such cameras, spectral cameras on a drone, you could fly over a group of animals and check differences in body temperature that would tell you some animals are sick.
I think it's being done, but that's well, we are talking about different spectra. You are talking about like heat emission, right? That's done in the long wave infrared, and that's a different kind of camera, a bit more like a bolometer. So I'm not familiar, but I mean, I can say from this point of view, I have read like many applications for like hyperspectral imaging, and as long as you find something unique within that spectral data, you can essentially measure it. As long as you can get the light reflected or transmitted from that object.
Please join me in thanking Jorge for his fabulous presentation.
Thank you. Thank you.
Thank you so much.
Well, our last speaker before afternoon tea, I think, might win the prize for the most cheeky title. Shall we go with that? We're going to welcome Ms. Maria Purnamasari. Maria has a Master's of Agricultural Science in Genetics and Breeding from UWA and a Bachelor of Science in Biotechnology from Atmajaya Catholic University in Indonesia. Maria is a recipient of the Australia Awards Scholarship and the Indonesia Endowment Fund for Education Scholarship, and she will be presenting today on Don't Shade Me, I'm Under Attack, Plant Genetics, Underlying Defence Under Contrasting Light Conditions. Please welcome Maria.
Good afternoon. My name is Maria Purnamasari. I'm PhD candidate at School of Agriculture and Environment, and today I'm going to talk about my research. But before I begin, I want to exactly highlight what I'm going to talk to you. So, similar with humans, plants that don't get enough sun easily come down with disease. And it is an important problem because it is one of limiting factors to increase planting density in the field. Therefore, the aim of my presentation today is to inform you how plant defense is weakened under shade. So I would like to use this opportunity to thank all the people in this slide because without them I would not be here, especially to my supervisors, Judith, Willie, Martin, and Janine, and also to my sponsor, Indonesia Government Scholarship LPDP. So I would like to start my presentation by introducing you to the subject of my study, Camelina sativa. It is ancient oilseed crop that famous for its excellent oil quality and its uses in biofuel production. It has many positive agronomic traits such as wide climatic adaptability and yield under low moisture. So, if you don't have enough rain, this crop is better option for you to grow than canola. However, it has been known that this crop has low genetic diversity. But fortunately, UWA has 30 unique germplasms that we can use to get a better understanding of camelina response to different environmental cues in order to promote a wider adoption of this crop. So the disease that I focus in my study is Sclerotinia rot, which caused by Sclerotinia sclerotiorum. I choose this necrotroph pathogen because it attacks wide range of crops, including canola, subclover, and chickpea. It caused huge economic damage, with more than 50% of yield losses has been reported in the field. And as you can see from this picture, the disease starts at the base of the stem, where plant usually getting shaded by its neighboring plant. The best strategy to manage the disease is using resistant cultivar. However, breeding for Sclerotinia resistant is being hampered due to lack of reliable screening and resistance dependent on pathogen variability. So now I'm going to give you a little background about my environmental factor, shade. So this picture gives you a comparison between sunlight and shade on irradiance and light wavelength. So there are three important light wavelengths in my study: blue and red, which is included in PAR, or the spectrum that plant can use for photosynthesis, and far red, which plant cannot use and they just transmit it to the environment. So under sunlight, PAR is around 100%, and the ratio between different light wavelengths is 1. This condition is similar with you grow 20 tomatoes plant in your field, and under this condition, your plant will grow normally. Under shade, PAR is reduced to 30% because neighboring plants use the blue and red light. And because they don't use the far red, the ratio between red light and far red light will reduce to below 0.5. This condition is similar with you grow 600 tomato plants per meter square. And under this condition, your plant will recognize the drop in red-far red ratio, and they will develop a new growth strategy called shade avoidance syndrome, in which the plant will increase elongation to compete with its neighboring plant, reduce branching, change flowering time, and reduce defense, which mechanism that I interested to explore. So when I talk about shade in my study, I talk about environment with red-far red ratio below than 0.5. So a facet of my PhD research try to answer three questions. First, to characterize UWA camelina genotype response to Sclerotinia. Second, to characterize camelina response to Sclerotinia under shade. And the last one, to dissect the genetic mechanisms underlying this response. So to answer the first question of camelina response to Sclerotinia, I inoculate 30 genotypes of camelina with 2 isolates of Sclerotinia. Isolate 1 is MBRS1, which is the most aggressive isolate from Western Australia. And isolate 2 is WW1, which is less aggressive isolate but has been known to cause different relative ranking. I also inoculate at 2 plant stages, cotyledon and flowering. And this slide shows you the result of camelina response to Sclerotinia. This graph shows you infection at cotyledon stage, with y-axis shows you disease severity and the x-axis shows you the genotypes. The blue bar shows you camelina response to most aggressive isolate, and the yellow bar shows you camelina response to less aggressive isolate. And this new graph shows you infection at flowering stage, with the y-axis shows you lesion length and the x-axis shows you the genotypes. And as you can see from these two graphs, we have a varied response for both isolates and for both inoculation states. But we can successfully identify a consistently resistant genotype, C370, as you can see from these pictures. And we also can find consistently susceptible genotype, C2305, as you can see from these pictures. And then we use these 2 genotypes as our parental lines to develop 106 F5 recombinant inbreed line genotypes to answer the last 2 questions. And then I inoculate this real genotype at flowering stage under shade mimicking condition and under normal light condition. And as we know that PAR, humidity, and temperature are important factors for disease development, I make sure to control these 3 factors so that the only difference between these 2 environments is only red-far-red ratio. I also collected genotypic data using .seq-LD to create 515 polymorphic markers in order to develop linkage map, and then combine the linkage map and phenotypic data to do QTL analysis to identify the genome locations affecting the resistant mechanisms. So, a QTL analysis is statistical method that link between phenotypic data and genotypic data to explain the genetic basis of variation in complex traits. And the result is usually presented as a plot like this, with the y-axis shows you the test statistic value, logarithmic of odds, and the x-axis shows you the chromosomal location, which measured by the molecular markers position. These horizontal lines mark the significant threshold measured by permutation test. And as we can see from this graph, this arrow identify the most likely position of a QTL because the peak of this QTL has high test statistic value more than the significant threshold. So let's go to the result. This slide shows you camelina response to sclerotinia under normal light. So this plot shows you disease severity on parental lines and real genotype. And as you can see from this plot and these pictures, that our parental line consistently showed contrasting disease reaction, while the real genotype show a level of resistance skewed toward the resistant parent. And we find a QTL that linked to this response, or camelina response to sclerotinia under normal light, at chromosome 9, which we call RSR, or resistant to sclerotinia road. And as you can see, RSR has peak high, that has high test statistic value more than the significant threshold. This RSR explains 14% of phenotypic variation, which is in line with previous study that say quantitative disease resistant to sclerotinia is governed by many genes with small to moderate effect. And the presence of RSR in the real genotype carrying resistant allele lead to lower disease severity or more resistant than real genotype carrying susceptible allele. Therefore, we conclude that resistance to sclerotinia is controlled by RSR locus in chromosome 9. And now this slide shows you camelina response to sclerotinia under shade. And this is similar graph as I showed you before, but then I added camelina response under shade. And you can see that both parental lines and real genotype increase the disease severity under shade as expected. And this is example of resistant parent C370 respond under normal light and under shade. And as you can see, there is drastic change in plant defense mechanism. Therefore, it is not surprising that we cannot detect the differentiate between resistant and susceptible parent under this condition, indicating that shade is important factor to control plant defense mechanism. So we conclude that defense to sclerotinia is compromised under shade. And how is camelina defense compromised under shade? First, we cannot detect the presence of RSR under this condition, indicating that defense to sclerotinia is weakened under shade by compromising RSR. And then, second, we also measure the slope value between disease severity under normal light and disease severity under shade. And we find a QTL that linked to this slope value at chromosome 15 that explains 17% of phenotypic variation. We call this QTL CIS, or shade-induced susceptibility, because the presence of this QTL in real genotype carrying resistant allele lead to higher slope value or more susceptible than real genotype carrying susceptible allele. Therefore, we conclude that in addition to compromising RSR, shade-induced susceptibility through cis locus at chromosome 15. So that brings me to the end of my presentation. To sum up, we find a significant variation in our camelina germplasm response to sclerotinia, in which we can identify a genotype that consistently resistant and susceptible and develop recombinant inbreeding population. And this real population help us to successfully identify RSR locus, which is important for resistance to sclerotinia. And we can use this QTL to develop camelina resistant cultivar. In addition, I also show you that camelina defense is weakened under shade, and we find two mechanisms underlying this response. First, RSR locus is compromised under shade, and second, shade-induced susceptibility locus cis. This finding has huge impact to better understanding disease epidemiology in the field. And to the best of our knowledge, RSR and cis are the first QTL find for camelina plant defense mechanism. So that's it from me today. Thank you very much for listening.
Any questions from the room for Maria? Maria, would you expect these sorts of findings to be mirrored in other sclerotinia susceptible species such as Canola cultivars?
Yeah, because camelina is also brassicaceae species like canola, so maybe we can get the knowledge from this RSR locus and cis also to develop canola-resistant cultivar.
Exciting stuff. I'm sure someone can ask a more intelligent question about disease-resistant genetics than I can. It would be hard to ask a less intelligent question than the ones I can ask. Please, have at it.
Sclerotinia, as you pointed out, is a very broad-based pathogen. Are there similar effects noted in other species attacked by sclerotinia, or do you think there's been unique dose?
So for RSR, I think it's only for camelina resistant to sclerotinia, but for cis, sorry.
Are there indications in the literature that other species react in the same way?
Oh yes. So sclerotinia, like I said, is making the plants to create quantitative disease-resistant phenotype, which there is no really significant, really resistant or susceptible, but it's like spectrum, varied response from very resistant to very susceptible. So camelina also show that phenotypic, the distribution like the other species. Is that your question?
Well, when the frequency of questions in the room dies down like this, it's usually a good sign that afternoon tea is on the way. But we have one more before we thank Maria.
Yes.
Hi, Maria.
Yes.
I see your population size is about 160. For a QTL analysis, statistically wise, the population size recommended is about 300 people. Although there are statisticians interested in that, but because they're comparing two conditions and it is holding in one and it is not holding the QTL, it's not holding in the other one, do you think that it will be linked to the statistical viability of the population size in Toronto?
Yeah, it is one of reason also, like you said. So the next study, I focus on creating more populations so that I can validate these QTLs in my populations. Thank you for the question, Pawinder.
Well, please join me in thanking Maria.
Thank you.
Thank you, everyone. Thank you, the speakers, and also please join me in thanking Sally for chairing the session and on time. Now we'll have a short break, half an hour. I hope you all had a good time chatting each other. We'll get some more opportunity for that at the end of the session, where there will be some drinks and finger food and so on. Let's start the second part of this series. I would like to welcome you all back and introduce the chair of the next session, Dr. Amin Mugera. Amin joined UWA as an assistant professor within the School of Agriculture and Environment in 2009. He is now an associate professor in the same area. He obtained his PhD in economics from Kansas State University in 2009 and a double Master of Science in Agriculture Economics and Agribusiness from Michigan State University in 2004. Amin has a broad research interest ranging from agribusiness, strategic management to production, financial analysis of agribusiness firms, and also speciality in smallholder farmers in a number of projects. He's also a joint team leader for the agribusiness ecosystem at the UWA Institute of Agriculture. I had the opportunity to work with Amin for a number of projects and traveled with him to different parts, including Africa and Asian countries. Amin is really a great resource person. He does conduct a number of master classes in agribusiness and entrepreneurship. So with that words, I would like to welcome Amin to chair the next session.
It's already on.
Okay, thank you.
Thank you.
All right, thank you, Professor Siddique, and good afternoon to all of you. So I'm just going to go right straight into why we are here. And in this session, we are going to have 4 speakers. Our first speaker is going to be Mr. Shamshad. And Mr. Shamshad is, before coming to UWA, he worked for the small dairy farm development and milk quality in Nestor, Pakistan. After completing his Doctor of Veterinary Medicine degree and lecturing at the University of Faisalabad in Pakistan, he moved to Perth to pursue his PhD in 2017. And today, he's going to be presenting on understanding diarrhea and worm resistance in sheep through gene expression. Please welcome Shamshad.
Thank you, Dr. Amin, for your kind introduction. Good afternoon, everyone. So today I will be talking about one of the major issues faced by Australian sheep industry and what are the best possible solutions for that problem. I would like to acknowledge all of my supervisor, all the institute and people who helped me through this project. So I will start my talk with the key message that a combination of genotypic and phenotypic selection in the sheep is the best and sustainable solution to the worm diarrhea problem. So before I get into the details, I would like to paint a brief background of what is happening. So the Western Australia climate has a typical Mediterranean type, which allows 2 nematode parasite larvae to flourish in winter rainfalls, which are picked by the sheep while grazing. These larvae become adult in the gastrointestinal tract of animal, and they start laying eggs. So while the animals suffer diarrhea, the eggs appear on the pasture again. So this cycle goes on and on. So the condition becomes more worse when the diarrhea attracts fly, in our case, Lucilia cuprina. The flies, they lay eggs, which become maggots, and maggots start eating meat, and the condition we call as a fly strike or meiosis. So combined, these 2 cycles lead to an annual loss of $600 million to Australian sheep industry in terms of treatment and control. So what possible solutions we have for these problems? So we can go for vaccination against these parasites. But so far, we don't have licensed commercial vaccines, which are still being developed. We can use enthelmintics. Enthelmintics are basically chemicals which are used to drench the animal to kill the worms inside the gastrointestinal tract. But worms are becoming resistant to these chemicals. Plus, another problem is enthelmintic residues, they appear in the meat, which is not demanded by the customers because customers demand chemical-free meat. So we can do the pasture management, which is a little bit expensive option because you have to move the animals around, so there is less contamination on the pasture, so to avoid the worms. Mulesing, that practice has been done in the past. In this practice, the hind quarter skin is removed, so the wool does not grow, and there is no soiling, and that avoids the chance to get struck with the flies. So use of insecticide to kill larvae on the pasture, again we face problem of resistance with regard to insecticides. So we are left with only one sustainable solution, that is selective breeding. So over 2 decades, selective breeding has led to development of one of the best resistant merino flock. But among some resistant animals, some animals are still they are still prone to develop diarrhea even with the less number of worms. So we hypothesize that that might be due to an impaired immune response. So this brings me to some of the highlights of the immune response that is required against these helminths. So both the branches of immune response, innate as well as adaptive immune response, are required to control the worms. So adaptive immune response is further subdivided into cell-mediated and humoral or antibody-mediated immune response. So cell-mediated immune response is further subdivided into T cytotoxic or T helper immune response. So T helper is further subdivided into T helper 1 and T helper 2 based upon the cytokines and antigen-presenting molecules they bind to. While the B cell or antibody-mediated immune response is divided into plasma cells, which are actually antibody-producing cells, and memory cells. So here we need a combination of innate plus antibody-mediated Th2 immune response for an animal to become resistant to the worms and diarrhea. But if the animal mounts a Th1 immune response, it becomes susceptible and might suffer a chronic diarrhea or worm infection. So aim of the study was to investigate the genetic mechanisms underlying resistance and susceptibility to worm infection and diarrhea. So here we have focused that the selection of animals so far has been done on 2 phenotypic traits, that are diarrhea or DAG score, which is measured on a scale of 1 to 5, 5 being the highest, and fecal egg count, which is number of eggs per gram of feces, 500 being the highest. So based upon these, for diarrhea and fecal egg count, we have 50 animal in each group in the high or low diarrhea and high or low fecal egg count. So here in the picture on the right animal, you see an animal with a DAG score of 4, and on the left you see an animal of DAG score of 5. So you see how this situation is terrible when animal is suffering from high diarrhea. So here you see DAG score 1 to 5, and in the lower graph you see that as the DAG score or diarrhea score increases, the probability to get struck with the flies also increases. So we monitored the diarrhea and fecal egg count on temporally. For the first 4 months of the trial, there was no grazing on the paddocks, and we treated the animals with monopental broad spectrum mentholmantic. And from March onwards, September, we monitored animal for the phenotypic traits I mentioned until we reached the end of trial, where we ethically slaughtered the animals to collect the tissues for further studies. So after collection of the tissues, we proceeded with some lab work for RNA extraction. Considering all the minimum standards, we used duodenum in this study, which is first part of small intestine. And then we proceeded with RNA-seq, which is one of the best technology available for gene expression studies. And we sequenced sample for at least 20 million reads per sample. And after that, we did data analysis. We used multiple software for transcriptome studies. And we used DSeq2 for statistical study of differentially expressed gene. And at the end, for the functional enrichment of genes, we focused on the biological processes, pathways, protein-protein interaction networks, and subnetworks. So moving toward the results, so we had 666 differentially expressed genes in diarrhea group, whereas we had 478 differentially expressed genes in fecal worm egg count group. So I will start with the comparison of low versus high diarrhea. So before I get into detail, I will give some brief highlights how diarrhea or worm expulsion can occur. So consider this as intestinal epithelium with the submucosal layer, and this is a muscular layer. So when there are worm larvae, either in the beginning they are expelled by the eosinophils, or their antigenic parts are taken up by antigen presenting cells like macrophage or dendritic cells to a nearby lymph node, where they are presented through MHC class II proteins to naive T cells, which are activated and become Th2 and cytokine producing cells, which activate B cells to become plasma cells, which actually produce antibodies. So the antibodies, along with the immune cells, try to neutralize the worms, so worms could be expelled. In case worm gets to establish, they will do the epithelial damage. Epithelium will become leaky, and animal will suffer diarrhea. So this is a brief overview of how diarrhea or worm expulsion can occur. So with regards to the genes, we are focused on the biological functions that are associated with these genes. So the biological functions which we see are just the tip of an iceberg, because they are controlled by multiple biological processes and pathways deep down. So we have to dive deeper to understand what biological functions are being controlled by what pathways and processes. So here in the low diarrhea group, we had multiple biological processes and pathways. If you allow me to summarize, they were related to immune response. So we also did network and subnetwork analysis that also yielded some similar results. So you will see some network diagrams in the coming slides, so don't worry, I will try to explain them. So the subnetworks were also associated with antibody-mediated immune response through MHC class II proteins. So in another subnetwork, we identified immune tolerance through tryptophan metabolism. So as the immune response is initiated, it has to remain in certain limits, because if there are no checks on immune system, that can become an autoimmunity or incorrect immune response. So here in the animal with low diarrhea, we also observe immune tolerance. So here again, I will bring back to the immune slide that we are seeing this part of immune response in animals with low diarrhea. So in high diarrhea, there were multiple processes, biological processes and pathways. So most of them were related to epithelial turnover, vessel development, or developmental process, because the high diarrhea was causing damage to the epithelium or the gut. So these processes were trying to fix the intestinal epithelium. So in the subnetwork analysis, we saw calcium ion mediated exocytosis, which we often see in secretory diarrhea. So coming towards the other comparison, when low versus high fecal egg count, in animals with low fecal egg count, we observed immune response basically related to leukocyte activation. To our surprise, we also observed interferon gamma regulation, which is actually a Th1 cytokine. That might lead to an immune response in a wrong direction. So that we assume that the animals with low fecal egg count, if they suffer diarrhea, this might be a possible reason that they are mounting a Th1 immune response. So in the network and subnetwork analysis, if I summarize these networks, so they were mostly associated with chemotaxis or migration of lymphocytes and eosinophils. So here in low diarrhea group, we see an innate immune response, basically with the chemotaxis of these cells that were controlling the worms, so they are not getting established. That's why they have low fecal egg count. But in the meanwhile, we also see regulation of interferon gamma. So that might lead to Th1 phenotype in these animals, and these animals might become susceptible. So in high fecal egg count, again, we have seen multiple biological processes and pathways. So they were related to extracellular matrix organization and biological adhesion. So these processes are mostly seen when there is an ongoing repair mechanism going on. So similarly, in the subnetwork analysis, we again see similar results of extracellular matrix organization and collagen fibril organization. So these genes are mostly activated when there is a damage process, in this case due to worms. The worms were causing the damage, and these genes were trying to fix this damage. So to visualize the genomic location of some important genes, we constructed this CIRCOS plot. So we were able to highlight that chromosome 14, 18, and 20 are important to start with, because they have a higher number of differentially expressed genes. So I have highlighted some important genes out of many differentially expressed genes. So in low diarrhea group, most of the genes, they were related to antigen processing and presentation, which is an important phenomena when there is worm infection. To start with, the animals with low fecal egg count have genes mostly with, they have a relevance to chemokines, attracting white blood cells to the site of infection. Whereas the high diarrhea and high fecal egg count, it's important genes that were related to some gene families like collagen, fibroblast growth factor, integrin, and serpin. So concluding these, some of the results, that the low diarrhea animals, they respond by humoral or antibody-mediated immune response through MHC class II proteins. And we also see immune tolerance through tryptophan metabolism. So one of the key genes that I identified in my study in low diarrhea group was ORDRB1, that has been associated with worm resistance in some other studies as well. So the animals with low fecal egg count have increased chemotaxis of white blood cells, for example, eosinophils and natural killer cells. So this might explain why they have a low worm egg count. So the animal with high diarrhea and high fecal egg count, they are totally relying on digestive tract repair and development, mostly through extracellular matrix organization. And we have seen epithelial turnover based upon the genes here expressed here, that epithelial turnover might be an explanation that these animals are trying to get rid of the worm by a turnover of epithelium. They are shedding the epithelium so they get rid of the worms. But meanwhile, they are also suffering diarrhea, which is not required. So the genes that I highlighted, especially those related to collagen family, fibroblast growth factor family, they indicate a fibrotic process going on. The fibrosis needs further explanation because fibrosis can remodel the immune system as well as they remodel the epithelium as well. So we need to further elucidate this fibrotic process. So the parallel work along with that, which I am currently doing, we are also focusing on the transcriptome of ileum, which is another part of small intestine, that if the ileum plays a role in diarrhea development. So we are also doing microbiome analysis along the longitudinal axis of gut. And we are also doing chromosome length genome assembly of the parasite species I mentioned to better understand the biology of the parasite. So with regards to future perspective, I would like to include some of the differentially expressed genes in our selection program. And as I mentioned earlier, that fibrosis, which I indicated that we have seen in animals with high diarrhea and high fecal egg count, it needs further elucidation. And because we have done this trial in totally natural conditions, so a trial in control condition can be conducted to narrow down the mechanisms further. So I would like to conclude my talk that along with selecting animals based upon phenotypic traits, we should also include some of the genes as a group when we are selecting the animals, so we have a better selection results. Thanks for hearing my talk. That's all.
Okay, let us thank Shamshad, and questions, please.
At the beginning of your talk, I think I heard you say that the resistant sheep with low egg counts were getting diarrhea.
Yeah.
I misunderstand. Is there a direct link? Is there a problem of diarrhea in the low?
Yeah, that's why we thought that the animals with the low diarrhea might have an impaired immune response. So we have highlighted, like I have seen that interferon gamma, which is a Th1 cytokine, is upregulated or regulated in this study. So that might be indication that the animals with low fecal egg count might have a high diarrhea. Maybe this is leading to a hypersensitive immune response.
And do you have when you started your experiment, did you know which sheep were which? Did you have those sheep identified?
Yes, I said, if you have seen that slide where we monitored the fecal egg count and diarrhea, so we were focusing on these phenotypic traits that these animals are high diarrhea and with low or high worm egg count. Yes, we did.
It wasn't clear in your results that there
Yep.
was a group with low fecal egg count
So basically, I use the grouping as high or low diarrhea irrespective of the other trait. Also, although we monitored that these are high or low fecal egg count or high or low diarrhea. So both traits were looked after in each group.
Phil?
Phenotypically, we see quite often that you can rid the sheep of worms
Yep.
with drench.
Yep.
And they'll stay clean for quite some time. But if you have a genetic gene resistance, allegedly based on the analysis that's been done of every meat count and so on, it's possible that the genetic resistance only, without drenching first, causes the diarrhea impact to occur. Does that make any sense to you?
Yeah, I'm getting you. Yes, can be done.
Just I'm wondering whether the incidence of a drench cleans the worms out.
Mm-hmm.
In the case that we did drench which lasts for 3 months.
Okay.
The Dynamax capsule drench. We did a three-part drench, so it had 3 active ingredients which last for the entire 3 months.
Mm-hmm.
And those tails remain clean for another 9 months, 12 months, maybe 2 years. We didn't have to drench after long.
So actually, our focus is like we want to move away from the use of anthelmintics. So keeping in view of clean, green, and ethical animal production. So I'm getting your question, but we.
For the genotypic side, I'm just making one try to separate out whether it's the genotypic side which causes the animals that have reactions to, and they might be resistant to worms, but reaction in their resistance to worms that causes the diarrhea, as opposed to any drenching.
It's a long question, so maybe in the in the session we can discuss in detail. Yep. It's a lengthy question. I understood some of those aspects, so we can discuss it in details.
Yeah, I think you can catch up later. So for the sake of time, we are going to move on. So thanks for that question. And yeah, let's put our hands together and thank Shamshad.
Thank you.
Okay, our next speaker is Mr. Hui Kao. Hui graduated from Capital Normal University in Beijing before coming to Perth in 2017 to complete his PhD. The focus of his research is to reveal how wheat grain protein accumulates during grain production and provide a perspective on energy use efficiency and protein content improvement for wheat-based agriculture. He'll be presenting today on why making protein fast can help modern wheat agriculture. Please welcome Mr. Hui.
Thank you, Amin, for the nice introduction, and thank you everyone for coming. Yes, so I'm going to talk in something about wheat grain proteins. Why making proteins fast can help modern wheat agriculture. So before I start my talk, I'd like to acknowledge the RTP scholarship for the financial support and the PB Center, which is the place I work in, and the agent for the technical support. Also, thank you to my supervisors, Harvey, Alvin, Nick, and the collaborators from the Multiple University, also other lab members. Yes, so I think many of you in this room are familiar with this dilution effect or the negative relationship between green year and green protein content. So I have some of the Australia cultivars here. You see a very clear negative correlation of these two among them. then as a scientist or a breeder, how can we balance this? Well, most of the case, the green yield wins the debate because growers are paid by yield. For them, the financial benefit they can get from the premier product content is not sufficient to cover the loss by the poor green yield. So, but the fact is, 1% increase in with green product content is potentially worth billions to Australia green industry. We can't just ignore this low protein issue forever, so we have to do something. Or maybe the easy way thing is just use more nitrogen fertilizer. That's true for general, more nitrogen supply can increase product content a bit. But the problem is nitrogen fertilizer doesn't come for free. It will cost gross income and is also not environmental friendly. For which case, so only about half of this nitrogen will get incorporated into biomass, which means the other half still remain in the lines of air. That will cause a serious air and the pollution. So how can we do that? How can we to avoid this low product content but without pollute the air, the environment? For example, you want to create a new variety around here, which will have the yield around 4 tons and the product content around 3%. So I think the potential solution can be either try to enhance the yield but keep the product content, or try to maintain the yield but increase the product content. But by either way, you might want to ask, why does making proteins cost the yield? Well, first of all, making proteins is not cheap. It's actually quite expensive. For the same amount, making proteins will cost twice as much as making starch. So that's why. And the second, different proteins cost different. So we know starch is just one starch. There's not much difference. But wheat grain has hundreds of different proteins. For example, the embryo has about 5,000 different proteins, and the number for the endosperm is about 3,000 and about 4,000 for pericarp. Also, if we separate these proteins by the functional group, we see some proteins will be more abundant than some others. For example, the starch protein one here, which is the predominant compound of the grain. So it can be up to 80% of total green protein. But these functional proteins are in much low abundance compared to this one here. And there's one more thing we can't forget. So we know some proteins are quite stable, but some other proteins not. So put all this together, some proteins will cost more some others. Now we know making proteins is quite expensive, but we need at least ask one more question if we really want to achieve this high protein thing. So what are the key determinants for protein accumulation? Someone's trying to find the answer from the gene expression level here, and some others trying to do the job directly from the protein bound level. And in some cases, people are doing both and trying to see how good these two can connect to each other. But the case is the correlation among these two are quite poor. We can only expect about 40% of the abundant variation by using the transcript data, which means there's still 60% sitting in the dark. Then is there anything we can do about that? So actually the protein bound comes from the synthesis rate and the degradation rate. So the data we call this protein turnover. So the question can be now, can be this protein turnover rate the key that we are looking for? We don't know yet because there's no such data out there we can use. So I decided to create one myself. So how did I do that? First, I used a stable isotope labeling technique that allows me to measure both the accumulation of newly synthesized proteins and also the loss of old existing proteins at the same time. So to begin with, I started labeling at 7 dps, 7 days post-anthesis, and then I collect samples after 3 days, 7 days, and 10 days labeling. And on the right-hand side, we see the nitrogen incorporation of 3 days about 20%, and then this number increased about 27% by 7 days and about 30% by 10 days. So at the end of this experiment, I quantified the protein abundance of 2,300 proteins and the nitrogen incorporation about 1,700 proteins. And using these two data sets, I calculated the protein synthesis rate and the degradation rate of 1,500 wheat grain proteins during grain development. And to summarize that, so we see the fastest synthesized proteins has a synthesis rate about 5.27 per day, while the number for the slowest one is only 0.057, which is like 100 times lower. And the median number for the synthesis rate is 0.35 per day. On the other side, we see the most unstable protein here has a degradation rate of about 0.94 per day, and the most stable protein of the wheat grain, we see it's barely degraded because they have a degradation rate very close to 0, and the median number for degradation rate is about 0.11. So when I visualize this data set by the functional groups, we see this one here. So I only show the 6 major groups, not the whole thing. But what I really want to show you is the variation of these 2 rates here among the different functional groups. We see the boxes of these top 3 groups are on the left-hand side of the dashed line, which is this median value here. And we see these 3 groups on the right-hand side of the line. So we see quite a bit variations here. And then storage proteins. So we expect very fast synthesis rates for storage proteins because we know the accumulation of them is one of the 2 main things during green feeding. So we see the synthesis rate of storage proteins is much higher compared to other functional groups. That makes sense. Again, storage proteins, we know they're supposed to serve as protein reserves for the later seed germination. So they should be like just immediately stored in the endosperm after biosynthesis in a matter of energy use efficiency. But this data tells us they also have a very high degradation rate compared to other functional groups, which means these stored proteins are not stable at all. And then to move on, so I have the data. Now it's time to test how well I can explain the protein abundance by using this 10-hour data. So how did I do that? On the left-hand side, I have the protein abundance changing data over time. Each line represents a protein, and the dashed line is the average number of all these proteins, and the shared area is the 95% CI. So on the right-hand side, I have the synthesis rate data and the degradation rate data. So we see the gap of these 2 lines here. This is the power that decides how fast the proteins accumulate over time. And we define this as the protein net accumulation rate. And then I use this green tissue specifically spray protein as an example here. So we see on the upper panel here, endosperm specific proteins has so this protein are accumulating much faster than the embryo and the pericarp specific proteins. We see these y-axis log2 transform, so the actually abundant change for some of these proteins in 10 days are nearly 100 times, but the number for these 2 are no more than 4. So we see a big difference here. On the lower panel, we see the net accumulation rate here for the endosperm specific proteins increasing over time. We can see a similar pattern here from the embryo specific proteins is getting bigger over time, but you look at the actual number here, so this number is much lower compared to the one we have here, so it's half, even less. And for the pericarp specific proteins, the number is low as well, and we see the gap here is narrowed down over time instead of getting bigger. So after this, I think the answer is clear. Protein turnover rate is highly associated with the protein abundance changes. It can tell not just the abundance, it also tells you how fast these proteins are accumulating over time. And then after this, we can do more than that. So we know both the protein synthesis and the protein degradation process are energy cost process. So if we can figure out how much energy wheat grain spend to each protein, will be fundamentally interesting and also benefit to the future wheat breeding program. So I did the calculation. I calculated energy cost for these 115 wheat grain proteins during grain development. And to summarize, so overall, the grain spent about 80% of ATP production for protein synthesis and another 2% for the degradation. So as I mentioned earlier, making protein is quite expensive. So here we see wheat grain spend about 20% of energy to make the protein only 10% in green wheat. So it's like twice. And of these 80% energy, most of them should go to starch synthesis because there's also a lot of starch accumulating at the same time. So again, if I present this data by breaking down to the different function groups, we get this one. So the axis here is the degradation rate, y-axis here is the density rate, and the size of the circle represents the energy, how percentage of energy used for each functional group. So it's quite complicated, but don't get scared. I promise you can follow. If we just focus on the storage protein here, which is the origin one here, so in overall, these storage proteins quite dominant on the energy cost for synthesis. From here, it spent about 9% of the total energy for storage protein at the earlier stage. Then this number jump up to 46% 4 days later, and then end up with 36% at the 70 dpm. On the lower panel, same, these storage proteins are also quite dominant here, which is about 14% of the total energy used for protein degradation. So from here, from this analysis, we learned that greens invest nearly half of the energy for just storage protein alone, which is a lot. And most importantly, this amount of energy here actually can cause the degradation of more than 20% newly synthesized proteins. So this big number, more than 1% I mentioned earlier. So to sum up, I got a few key messages here. First of all, so protein turnover rate provides a new insight into how different sets of proteins accumulate. It can tell how fast these proteins accumulate over time, rather than just the final protein abundance. And second one, wheat grain storage proteins are not stable. They have a very high degradation rate compared to other proteins. So they are not just like made and stored as the ideal scenario it should be, but they are not just not stable as we thought. And third, wheat grains undergo significant fertile cycling of protein turnover during grain feeding that incurs the unnecessary degradation of over 20% storage proteins. This is a huge loss of grain protein content and also a big energy waste. And the last one, I think in the future, those approaches that can block these fertile cycles or differentiate express more stable proteins that should increase protein content or improve the energy use efficiency. So then bring it back to the figure I showed you at the very beginning. This has been looked again. So we know there's a 20% storage protein degradation here. If we could block this one here, so we can make the grain protein content increase from 10% to 12% without making new proteins. So we don't have to make proteins faster. We don't have to use more nitrogens. If we just block this thing here, we can jump here to here without extra cost. Again, if we can take one step further, if we could have wheat grain to reallocate energy saved from here to make new starch, we may even be able to increase green at the same time. Then we don't have to suffer this negative correlation anymore. Thank you.
Thank you, Kyle, for telling us about making protein. So, questions? How we can make protein? Yeah?
So, in the last statement that you just made about how we go about changing PE4, what's the scientific approach that we would take to do that?
Well, yeah, that's a good one. Thank you. So I think now we have this all the useful data here. We know there's about 20% degradation there. So I think in the next step, we're going to looking for potential kind of cultivars. They have some proteins have very kind of low degradation rate. Then we can count across this protein into the target variety we can use to make this protein more stable. Or otherwise, or the other options, we can use some CRISPR-9 technique to knock down some of very fast turnover proteins to save energies. And then we can increase the protein content at the end, but either way.
Thank you. The grain protein and yield has been a topic of research in wheat and many other crops for a long time. And of course, I do respect that negative correlation between grain protein and yield. But the breeders have been able to break that. And there are varieties, I'm sure we can find the names, which has got high yield and high protein.
Yep.
When I say high protein, which is a respectable standard, perhaps you may need to look at those genotypes.
Yeah.
And then study what the stress has been
Yeah. Yeah, that would be so that would be in the future where we're looking for those have both high yield and both high protein content. Look at those storage proteins, how fast they turn over. If they have very kind of lower degradation rate, which makes sense, then we can use those as a potential target that we can work with to finally improve this.
Especially in durum meat, again, the protein is very high. You'll find that in there. Look at that as an example as well. Red meat and durum meat.
Yeah. Thank you.
An alternative approach might be to hold the genotype constant and vary the yield potential agronomically and see if the same patterns occur.
Excuse me, can you repeat that again? Excuse me, can you repeat the question again?
Repeat the question again.
Yeah. I didn't follow that yet.
It was really a comment, but an alternative way of looking at the turnover is to hold the genotype constant and alter the yield agronomically so that you can see are the patterns the same when the genotype is constant but the environment is different.
Because these proteins stability get affected by multiple factors. So this is just one thing we're looking for. Yeah, that's true. I agree with that. There's some other environmental issues also will affect to that. So we will look at that later. So bring up the genome data and the environment data, see which one affect to these things related to more. Then we can decide to which kind of strategy we're going to apply for the future breeding process. Yeah. So this is the very fundamental data here. Then we add up more, then make more kind of robust in the future.
I have a quick question, maybe out of ignorance, but you say that the making of protein is expensive.
Yeah.
And I understand you're talking in terms of energy efficiency.
Yeah.
But as an economist, I couldn't, stop thinking. If you think in terms of dollar value and you say it's expensive, what does that mean?
Because, so we know so there's something in protein, right? So when you're making proteins, it will cost. When you add amino acid to the sequence, it costs the energy. But also, this protein is not stable. After for a while, they will degrade. That's going to cost extra energy. That's why making these proteins expensive. It's not like we're making product which is built up. Okay, that will last forever, but not this case. That's why this protein costs quite a lot because they are consistently changed and renewed. Yeah.
Thank you.
Thank you.
So let's put our hands together and
Here you go. Hello.
Thank you.
All right, thank you. Yeah, our third speaker is going to be Mr. Mohammad Golam Kibria. And after completing his Bachelor of Science in Agriculture and Master of Soil Science from Bangladesh Agricultural University in 2015, Mohammad was appointed as a faculty member at the Department of Soil Science at the university. He came to Perth in 2017 to complete his PhD, and he is currently working on managing wheat growth in acid soil by applying magnesium through foliar means. He'll be presenting today on foliar magnesium application enhances wheat growth in acid soil. Please welcome Mr. Mohammad. Yeah.
Good afternoon, everybody. Thanks, Dr. Amin, for introducing me. Today, I'm going to talk about a very significant problem experienced by the wheat industries in Western Australia, which is soil acidity. And my key message of my today's talk is highlighted in the title that foliar magnesium application enhances wheat growth in acidic soil. At first, I would like to take the opportunity to acknowledge my supervisors, the funding authority, and the mentioned people in the slide for their continuous support throughout the project. So let's begin what we actually done. So why we actually did this research? As I mentioned that soil acidity significantly affects with growth in acidic soil, and what actually plant experience when they are exposed to acidic soil. You can have a look that the below ground part, that means the roots are much more affected than the above ground part. That means the roots are the most adversely affected part of the plant. And due to this region, wheat industries is actually experiencing around $0.5 billion loss annually. And what's the main reason behind that? Firstly, the increased toxicity of different elements, say aluminum, manganese, and iron, and aluminum toxicity being the major limiting factor in acidic soil. Simultaneously, the decreased availability of other essential elements, say calcium, magnesium, phosphorus, and molybdenum. And the main reason is the agricultural approaches practiced by the farmers in Western Australia or all over the world, as well as the low pH buffering capacity of soil, actually making the soil acidic. Let me explain you the causes of soil acidity in more details. So in agricultural field, like we have two different crops, so one is cereals and another is legume. Firstly, acidic precipitation. Second, application of ammonium-containing fertilizer. We are adding ammonium into the soil. Nitrogen leaching, which are actually derived from the organic matter decomposition in soil. Nitrogen fixation by the legumes, which also making the soil acidic. Less anion uptake by the plant, as well as more hydrogen ion released in the soil solution due to more cation uptake by the plants. Actually, these are the basic cations in soil, and the plants are actually taking up those basic cation in the above ground part. And finally, the removal of products, we are actually harvesting the above ground part with the basic cations leaving the soil acidic. So what are the available management practices till now we are actually doing in the field? Firstly, the liming. This is the most common and effective strategy to ameliorate acid soil, but as soil acidity can occur in both topsoil and subsoil, it involves huge cost to ameliorate subsoil acidity because we need to incorporate lime into subsoil. As in another option, magnesium, that's our focus element today, that magnesium can play a protective role against aluminum toxicity, and it can contribute to develop the root growth at inadequate magnesium condition. But if we apply magnesium to soil, you will experience two problems. Number one is soil fixation, and number two is the leaching loss from soil. But if we apply magnesium to the leaf, we can actually easily avoid this true problem. And in case of wheat, this will be more advantageous for wheat because the leaves are amphistomatic. The stomatas are distributed on the both sides of the leaf, which actually help the plant to absorb the nutrient more effectively compared to other plants. But very limited information is available on the effectiveness of foliar magnesium on increasing wheat growth in acidic soil, although some literatures are already published on the hydroponic culture as till now. So my main aim of my talk today is to characterize the role of foliar magnesium application in enhancing wheat growth in acidic soil, and we identified three different questions to acknowledge this aim. Number one, does foliar magnesium application contribute to increase wheat growth in acidic soil? Second, does genetic aluminum resistance with foliar magnesium application contribute to enhance wheat growth in acidic soil? And finally, the mechanism. How does foliar magnesium contribute to increase wheat growth? Let us go for the question one. Here we assess the effectiveness of magnesium sulfate as a source of foliar magnesium to enhance wheat growth in acidic soil. In a two-factor experiment, in factor A, we had foliar magnesium. In factor B, we had soil treatment. Under foliar magnesium, we use 4 different doses of magnesium, 0, 50, 200, and 1000 milligram of magnesium. In a soil treatment, we use 3 different soil, less acidic or slightly acidic marine, moderately acidic kalani, and highly acidic South Caribbean soil. With moderately acidic kalani soil, we added 50% of recommended lime dose in subsoil. And in case of highly acidic South Caribbean soil, we added 4 milligram of magnesium and 50% of recommended lime dose in subsoil. So we had 6 different soil treatments. We applied magnesium to the foliage at 2 and 4 weeks after sowing, and we harvested our plant at 5 weeks after sowing. Let's see what we actually got. The shoot dry wet. As I told, we had 4 different doses of magnesium, 0, 50, 200, and 1000. We plotted shoot dry wet against that. That means in shoot dry wet up to 0.35 gram. In control, we got around 0.29 gram of shoot dry biomass. At 50, it increased by 7%. At 200, it increased by 14%. So what happened for 1000? Does it actually increase or decrease? It is decreased, but still it's increasing 5% compared to the zero foliar magnesium treated plants. In the soil treatments, we had 6 different soil treatments, and similarly we plotted shoot dry wet in y-axis. In slightly acidic meridian soil, the shoot dry wet was like bit satisfactory. In moderately acidic colony soil, that declined significantly. And when we applied lime with that, 50% of recommended lime, it just increased by 17%. And in case of South Caribbean, the highly acidic soil, the shoot dry wet was the lowest, and the 4 milligram of magnesium increased the 15% of shoot dry biomass, and in case of lime, it increased by 22%. Let's see what happened for the root dry wet. Similarly, we plotted root dry wet against foliar magnesium application, and we got the similar result like as the shoot dry biomass, which is actually 14% increase in shoot dry biomass and root dry biomass, both at 200 milligram of magnesium application. And in case of soil treatment, similarly, we got that meridian just a bit good. And in case of colony soil, it declined and increased by 13% when we applied lime to subsoil. And in case of South Caribbean soil, it also increased by 14% in lime and 17% in magnesium amendment. So the lime is still the best possible option to ameliorate soil acidity. So I'd like to conclude the first question answer, that does foliar magnesium application enhances weed growth in acidic soil? My answer will be yes. And the dose can be 200 milligram of magnesium per liter, but the increase is not to the same extent as subsoil liming. Secondly, here we assess the effectiveness of foliar magnesium in 2 different genotypes differing in aluminum resistance capacity. In a 3-factorial experiment, in a first factor A, we used the different genotypes, ES8 and ET8. One is sensitive and another one is resistant. We used 2 magnesium doses, 0 and 200. This dose we actually grabbed it from our previous experiment. In a soil treatment, we used the moderately acidic colony soil, and we added lime and 20 milligram of magnesium from 2 different sources to the colony soil. Similar to previous experiment, we applied magnesium at 2 and 4 weeks after sowing, and we harvested our plant at anthesis stage. Let's see what we actually got, shoot dry wet and total leaf area. Here we got only 2 doses, 0 and 200. We plotted shoot dry wet in y-axis. When there was no foliar magnesium, you can have a look that aluminum resistant genotype produced more shoot biomass compared to the aluminum sensitive one. And when we applied magnesium at 200 milligram of magnesium per liter, it increased by 42% in sensitive genotype and 24% in resistant genotype. In case of total leaf area, we got the similar finding like that. And you can see that aluminum sensitive genotype, the percent increase is proportionally more than the aluminum resistant one. In case of subsoil root growth, as I show you in the first slide, that root is the mostly affected part in the acidic soil. So what actually happened in subsoil root growth when we apply magnesium to the foliage. Specifically in the subsoil root dry wet, we got the similar finding that aluminum sensitive and aluminum resistant genotype increased both significantly compared to the 0 foliar magnesium treated plants. And in case of subsoil coarse root length, the root length also higher in aluminum resistant genotype compared to the aluminum sensitive one, and the percent increase is also higher in the sensitive genotype compared to the resistant genotype. So I'd like to conclude the second question here, that does foliar magnesium can increase the wheat growth of aluminum resistant genotype? Our answer is yes. Aluminum resistance coupled with foliar magnesium can contribute to increased wheat growth in acidic soil, and aluminum sensitive genotype responded proportionally more compared to the aluminum resistant one. Finally, the mechanism, how foliar magnesium can contribute to increased wheat growth in acidic soil. Here in this experiment, we assess the effectiveness of foliar magnesium on root exudation. So why we are actually interested in root exudation? You can have a look in the picture that aluminum, trivalent aluminum are mostly toxic to the plant species. When the plant exudates the malate and citrate, they actually combines with the trivalent aluminum and forms aluminum complex. Those are non-toxic to plant root and which actually allows effective root growth in acidic soil. So if we can see that foliar applied magnesium can contribute to increase the exudation of malate and citrate, we can say that this could be one of the mechanisms to increase weed growth in acidic soil. Here we use the moderately acidic colony soil as well as the magnesium sulfate as a source of foliar magnesium here. In a 2-factorial experiment in factor A, we use 3 different doses here, 0, 200, and 500. And we use 2 different genotypes, ES8 and ET8. Similar to our previous experiment, we applied magnesium at the same date. We harvested our plant at 6 weeks after sowing, and we analyzed the root exudate carboxylates at harvest. I'd like to show you the root growth in both topsoil and subsoil. In the aluminum sensitive genotype, you can have a look that both of the foliar applied magnesium increased the root biomass compared to the 0 foliar magnesium treated plants. And the similar results we actually got in case of the aluminum resistant genotype as well, that foliar applied magnesium increased the root growth in both topsoil and subsoil by foliar magnesium application. So the root exudate carboxylates, so our focus today. Firstly, 3 different doses of magnesium, 0, 200, and 500. We plotted malate up to 12 at y-axis. When we applied 200 milligram of magnesium, you can see that the exudation of malate was almost double in 200 milligram of magnesium compared to 0. And what happened for 500? It also increased compared to control, but not to the same extent as the 201. In case of citrate, the similar finding actually got that application of magnesium increased the citrate exudation at 200 and 500 milligram of magnesium. So we would like to say that foliar magnesium application at 200 milligram per liter increased the malate and citrate at least by 90% compared to 0 foliar magnesium treated plants. So I would like to wrap up my presentation today with the key message again, that foliar magnesium application increases with growth in acidic soil. We had 3 questions. And the first one, does foliar magnesium application enhances with growth in acidic soil? Our answer is yes. With growth in acidic soil can be increased by applying magnesium to the foliage, but that is not to the same extent as subsoil liming. Does genetic aluminum resistance coupled with magnesium contribute to increased weed growth in acidic soil? The answer is yes, but the aluminum sensitive genotype responded proportionally more than the aluminum resistant one. And the foliar applied magnesium contribute to improve weed growth in acidic soil actually by increasing the exudation of malate and citrate. Thank you so much for your patience hearing.
Thank you, Mohammad. Questions? Ken?
Thanks very much. My question is, there'll be 2 parts to it. Why you focused on magnesium, and why is magnesium causing an increase in citrate and malate? Is this like a plant immune response? Because other fertilizers have been known to elicit plant immune responses. So, has it nothing to do with magnesium per se? Is it a plant immune response to the application of fertilizer?
Thank you. Sir, we actually used magnesium because normally we apply lime to the topsoil by top dressing of lime, and it actually take longer time to reach the subsoil and interact with the subsoil acidity to manage that crop production in acidic soil. But if we apply lime, say we do not need to apply lime very frequently. We can use the magnesium as a different approach or another approach to as a medium-term strategy actually to manage the crop production in acidic soil. And the magnesium actually, this is very highly the high mobility in xylem and phloem, and when this root exudate carboxylates, this carboxylates actually increases when the magnesium is available in the plant, and this exudates actually contribute to increase when there is adequate amount of magnesium in plant species, and they also releases in acidic soil to interact with the trivalent aluminium and making the non-toxic aluminum species. Exactly, yes. I would like to add that we did another experiment we have not presented here. We used two different sources of foliar magnesium, both magnesium sulfate and magnesium chloride, to see whether it is the effect of magnesium or only the magnesium sulfate. But we did get the similar result using magnesium sulfate and magnesium chloride at the same dose. Yes, exactly, yes, foliarly. No, we didn't try it here.
One more question? You can take one more question here.
The subsoil liming, was this done in pots or was this done in...
Yes, yes.
Because we know that deep ripping can have a dramatic effect on yield, independent of the...
Yes, subsoil, the liming was done in the subsoil directly when we mixed the subsoil and the layer of 5 millimeter of topsoil in the potting mixture, and we restructured the soil profile in the glasshouse condition.
Okay, so let's thank Mohammad for this wonderful presentation. All right, our fourth and final presenter is Mr. Omar Anwar. Omar completed the Bachelor of Science in Electronic Engineering in Pakistan and Masters of Science in Embedded System Engineering at the University of Leeds in the UK. Before starting his PhD at UWA Department of Electricals, Electronics and Computer Engineering, Omar worked as an academic and as a researcher at multiple universities. He is also the recipient of the WA's Government Science Industry PhD Fellowship, and today he will be presenting on remote beehive health monitoring using long-range communication. Please welcome Omar.
Hello everyone, welcome to the last presentation, and refreshments are just around the corner, so cheer up, you have almost made it. Okay, so as Dr. Amin mentioned, my work is on remote beehive health monitoring, and it is supervised by Dr. Gino, Adrian, Rachel, and Amitawa. My research is funded by CRC for honeybee products, and today I will be talking about some of the science which goes behind the art of beekeeping. Humans and honeybees, the story is not new. Egyptians had honeybees while they were building the Great Pyramids. Domestic bees have been with us for thousands of years, and why are we worried about them now? It is actually our survival, the human survival, which depends upon honeybees. Almost 1/3 of what we eat comes from pollination, and honeybees are the single most important pollinator. And recently they have not been doing very well. The fires and the climate change has adversely impacted a lot of their food resources. And then on top of that, there are some deadly diseases which can actually spread very fast and wipe out entire colonies. Domestic bees are very fragile and need a lot of care and attention. And beekeepers put in a lot of hard work to keep their bees safe. While inspecting the hives, they open the hive, they go through it frame by frame, and it takes a lot of time. Also, after every inspection, bees actually have to repair the hive from the inside. So we cannot do this inspection very regularly. Hives are often located far away in the fields for pollination or in the forest for collection of honey, and they are hundreds of kilometers away at times. So beekeepers have to travel these long distances to go to the hives and see if the bees are doing well or not. And after all this hard work, there's still a chance that they may miss something. There's a chance of manual oversight. Before we go any further, we actually have to understand the life cycle of a worker bee. It starts with a queen, the single most important bee inside a hive, whose only job in her 5 to 7 year life is to lay eggs, to breed. Eggs, they convert into larvae, and the pupate, this actually takes about 3 weeks, and after 3 weeks they hatch as hive bees. These hive bees stay inside the hive and do hive chores such as cleaning the hive, attending to the queen, to the brood, and maintaining the temperature. After about 3 weeks, these bees convert into foragers, and the only job of foragers is to go out and find food. which is pollen and nectar. The food they bring back, it is used by the hive bees, the brood, and it's also used to be stored to be used in the winter. After about 2 weeks of forager activity, the foragers die. So bees have a relatively short life cycle, from egg till death about 8 weeks. The problem happens when environment starts to impact them. For example, harsh weather conditions can kill the brood, or if we are using some not suitable pesticides, that can kill the foragers. Or if there is no food to go around, foragers will not be able to bring anything back, and that can kill the hive bees. In a good healthy hive, the death rate at these stages, brood and hive bees, that is negligible. If we take a look inside the hive, this is a frame full of brood. All the brown part is brood which is ready to hatch. On top we can see some white cells which is cap nectar, and there is some pollen which is in yellow. Here are some bees which are hatching from the cells, and here's a frame which is full of cap nectar, or honey as we call it. So when it comes to electronic monitoring, there are 3 fundamental components these systems should have. Number 1, sensors placed inside or around the hive. Number 2, a communication system that should carry the data from sensors to the beekeeper, and a user interface which beekeeper can use to access this information. We have advanced components such as smart processing of the sensor data. We can have a network of sensors at a hive site, and we want long distance monitoring, preferably global, where a beekeeper can access the status of the hive using internet from anytime, anywhere. And then there is health and status prediction, which is a hot research topic these days. The major aim of these systems is, number 1, round-the-clock monitoring. Since we have sensors inside the hive 24/7, they can check the status of the hives continuously. And this actually increases the chances of disease detection, because we can pick them up timely. We don't have to wait for the inspection, which happens every week or every 2 weeks. We also expect these systems to not only tell us what is going on in the hive right now, but we also want them to warn us in advance if something bad is about to happen. So we want this prediction capability. What a beekeeper wants the most from these systems is to save time and money. And they will only invest in these systems if they will save them cost in the long run, which also means they want to minimize the use of labor. This brings us to the question of what sensors should we use inside the hives. So the first study of checking the temperature, monitoring the temperature inside the hive was conducted in 1917. And since then, a lot of sensors have been tested for their relevance with the bee health. Some are relevant, some are not. I have divided them into 3 different categories. We will actually be discussing temperature here. Temperature, a very high relevant parameter with very high relevance, because it provides us information about brood health and colony strength. For brood to hatch properly inside the hive, the temperature in the brood area should be 35 degrees centigrade. And bees work very hard to maintain this temperature. Let's assume this room is a hive and we are all bees, and we have to maintain a temperature of 35 degrees without any air conditioning. If it gets too hot inside the room, some of us will go out, open the door, and use our hands to make some airflow inside. That's hard work, right? But bees do exactly that. They go outside, they use their wings to cause a flow of air from outside the hive into the hive. This is called fanning. And if the temperature gets too cold, we will all cluster together. Provided there are no COVID restrictions, we will come into the middle of the room and use our body heat to keep the center warm. That is what bees do during cold days. They use body heat metabolism to generate heat and keep the brood warm. And this is only possible if bees are present in great numbers. If bees are healthy, if the hive is strong, they will be able to regulate their temperature to a steady 35 degrees centigrade. Otherwise, we will see variations. And what happens if the bees hatch at temperatures other than 35 degrees? Those bees have a problem. They are like bit like us, the academics. Disoriented, with little sense of direction. When they go outside, they spend a lot of time roaming around without actually knowing what they are doing. And at the end of the day, they bring back very little food. So a few of them are okay, but too many academic bees and the hive is doomed. So that's why it's very important to regulate the temperature of the hive. So is every sensor which is important, is it also practical? Unfortunately not. We have to look at a few different aspects to see if a sensor can be deployed or not. We will be discussing internal imaging in this case. On paper, it looks very good. Put a camera inside the hive and you are able to see what bees are doing. Job done. But practically, cameras do not work inside the hive. Number one, you need light inside the hive and it is very dark. If you put some light source, it becomes invasive and bees don't like that. Let's say somehow we get past this problem of light. Bees have this habit of putting wax on everything. So after a few days, the lens of camera is covered with wax. You cannot see anything. And cameras are also very power hungry. And if we want to process, extract information from the videos or images, it takes a lot of computation. So not everything which is relevant is also can be practical. So we have to find a good balance between relevance and practicality. Coming to our research, what we are trying to do? We are trying to answer 3 questions. Question number 1, how to classify beehive health state using data from multiple sensors. So we are investigating different sensors for their relevance, and we are also trying to find out which sensors complement each other well. If we are trying to record audio signals inside the hive, the microphones are very good at picking frequencies of 100 Hz and above. If we use accelerometers, they can actually detect low-end frequencies. And both of them put together give us a very good picture of the entire spectrum. Question number 2 is how to improve the classification accuracy given sensor limitations, practical constraints, and hostile hive environment. So we are testing different sensor configurations inside the hive while trying to find the right balance between cost, power, and practical feasibility. Question number 3, how to communicate hive data effectively over long distance for decision making. We are trying to find out what is the vital data from the hive that we should transmit, what should be the optimal sampling rate for the sensors, and what features should we extract inside the hive and how to transmit those features using least amount of power. There are many challenges associated with this work actually. Number 1, selection of parameters. As we have already seen, not everything which is relevant is also practical. There's also this question of cost versus accuracy. Good sensors, everyone wants to use them, but if they are costly, they are of no use because beekeepers do not want to spend a lot of money on these systems. So we have to choose sensors which are cost effective and work with whatever accuracy they have. Remote monitoring comes with its own set of challenges. Number 1 is power consumption. Out in the field or in the forest, there is no AC power available. So these systems should be efficient and they should last as long as possible using the small battery they have. Communication is another problem. The 3G or 4G coverage, if you move out 200 kilometers out, it is very patchy. It cannot be relied upon. If we go for satellite communication, it is expensive. NB-IoT, Narrow Band Internet of Things, it's a very good alternate. And here's the coverage map of Telstra for Australia, and this is very good coverage. But NB-IoT has a limitation. It cannot work with large amounts of data. So we have to have small amounts of data if we want to make use of Narrow Band Internet of Things. Okay, monitoring systems with decision-making capability. This is the most challenging task. We use machine learning, which actually works by going through examples containing both input and output. Input in our case is data which is coming from the sensors from inside the hive. Output is assessment of the beekeepers for the very same hive. And with enough examples, these machine learning models learn to translate sensor data into assessment of hive. This assessment which looks like assessment from a beekeeper. So these systems actually try to mimic the beekeeper. And this assessment from beekeepers, our ground truth, actually comes in forms like these. We have to actually ask beekeepers to fill out these forms whenever they are doing the inspection, and then we use the data collected from these forms to train our machine learning models. There is no publicly available training data set. Whatever data we need, we have to collect our own data so that we can collect our models. Coming to the progress, okay, when we started, the first system I made was actually quite big, and it was meant to go into the middle of the hive, which beekeepers did not like because that is where the brood is. So now we have an improved system which is much smaller, and it sits nicely on the side of a frame, and it can be deployed, and it does not get in the ways of bees that much. First system I designed, it died after 20 hours inside the hive. We don't want that. So after significant improvements, the new system can collect data for up to 20 days. And since we are using small solar panels, theoretically it can collect data forever, because those solar panels keep it charging as we go. We are using feature extraction and reducing the sensor data size from 6,000 bytes to around 91 bytes. And this compression is vital because we want to make use of narrowband Internet of Things and LoRaWAN, long range wide area network. Both of them have good range, but they require data to be small. We have designed our onboards which have which can use actually both of these communication technologies. We are evaluating 9 different sensors in our design and more than 40 features for their usefulness with the bee monitoring. To conclude, it has been a journey of many findings. A lot of things I found out were about what does not work. A few of them, what does work. I have enjoyed excellent support from my supervisors, my funding body CRC for honeybee products, and the beekeepers I'm working with. And with their continued support, we hope to come up with a system which will be able to take better care of honeybees, hence improve the pollination and secure our global food supply. Thank you.
Thank you, Omar. Questions? Yes?
Sorry, can you please be a little louder?
How could all these sensors interfere?
It can. First thing we want to make sure is that these sensors do not get in the... Sorry? Yep. First thing we want to make sure, as for example, there are some counters that are very good at finding out how many bees are going in and out of the hive. But what these counters do is they actually have to create these narrow channels where the bees have to pass through, and this actually obstructs their movement. What we are trying to do is we are actually choosing only the sensors which do not get in the way. We cannot say that it will be absolutely no problem, because if we put something inside the hive, it will create some problem for the bees. The idea is to have more benefits than having disadvantages. So we want, in long run, we want to benefit the bees. So if our sensors are small and sit on the side, they do not generate heat or light, they should be okay.
Questions?
Yes.
Omar, do you have a feeling, I'll ask Amin questions, do you have a feeling of what the cost might get down to before the beekeepers want to take on?
Okay, beekeepers do not want to spend in the long run. I mean, they are okay with spending initially, but if there are ongoing costs, they don't like that. With satellite communication, that is the major problem. They have to pay monthly bills. Ideally, we would like a system to be between $100 and $200. And it again depends. For example, when we started with the cell phones, they were really expensive, but we went into mass production, they became cheap. Same with this technology. As we progress further and more beekeepers want to start using them, the cost will come down significantly.
Okay, I have a question
Sure.
regarding to AI, artificial intelligence that you're using in collecting the data. Do you have enough samples so that you can be able to collect over time to be able to have the data for training and for doing what you have to do?
It is a very good question, because this is the most challenging task. Since there is nothing available publicly, we are halfway through and we have started collecting data. We started with 1 system, now we have 5. We may deploy more, and that is the aim, that in next year or so we will have enough data and with enough examples to train this AI. Will this work everywhere? No, because we are only collecting data from Australia. It may have its problems when we move elsewhere. So that is always the limitation of these systems, but we are hoping that with enough data we will have something at least which works well in Australia.
let us thank Mr. Omar for his wonderful presentation.
Thank you.
Thank you, Amin, for sharing it nicely. I don't think I have given you a bottle of wine. Simon, did I? No? I'm very glad. I feel I'm very glad. So this is for you to come and spend time. Well, we're coming to an end. I got a few small things to tell before we go for a drink. So let's thank the speakers of the second session and Amin for doing a great job there. Thank you. I also want to thank the IOA team. Many of them are here. Rosanna Candler, let me get it right, Candler. Then Diana is here. Laura, who worked hard to get this organized. She's not with us. Laura Skates, and also Cora. She's still working in the office there. So thank you for all putting this together. Another person I would like to thank for the last 14 years I have been thanking is Professor Graeme Martin. And you know that these students were trained by Graeme in terms of scientific presentation and so on. So you can see that, of course, the students are absolutely brilliant, but Graeme fine-tuned them to make sure that they give the right pitch, the right time, and a take-home message. And you all will agree with me that the presentations were excellent. And let's give one more applause to all the students. And also, I'll give you a wine shortly, Graeme. And also, there are a number of PhD students in the back, and you will be one of them next year and the following year. So there's a lot to learn. I always tell my students, and we don't have many undergraduate students, coming for a lecture like this or a seminar like this, you learn lots than what you would have learned otherwise sitting in your lab and say, okay, I lost 2 hours. But within these 2 hours or 3 hours, you would have learned a lot, and which is much better than you learning from your supervisors, because you can easily compare with the students and the topics, a range of topics, from genomics to application of fertilizers to the honeybee thing and various aspects. So this is the type of research going on at the University of Western Australia, and it comes from different faculties and schools. We hope to have more students in the next time. Now, we recently launched our website, so if anyone wants to go and look at a revamped website, and it is an embarrassment because for the last 4.5 years, I have been wanting to get this done. Finally, we got it done. So we did, that number of people worked hard. So the new website is there, and we will continue to improve that, particularly for the forthcoming events and things. You need to look at that. For that, we have 2 upcoming events. Again, the COVID hasn't helped us to spread that around. All are compressed. For example, this postgraduate symposium was supposed to occur way back in June. Now we have the first one coming is the Industry Forum 2020, Climate Change and Agriculture, Challenges and Solutions for Australian Farmers. That will be at the University Club of WA Auditorium on 28th of October, and 1:30 p.m. registration, so on. And there's a sundowner. Already the online registration is reaching peak, and we have some COVID restrictions. Hopefully the Premier will release that bit more and we can accommodate more people by that time. The second one is the Hector and Andrew Stewart Memorial Lecture, which will be presented by Dr. Graham Robertson, and he will talk about food security, agriculture in Western Australia. So that will be an interesting events which you need to note. I think that's all I have to say. And once again, thank you all for coming. And there's refreshments and some finger foods, the foyer. So please join all of us, and let's celebrate the success of the students and their supervisors. So thank you, everyone. That close.